Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step on inside and we're going to go into section 4.9 in the Big Ideas Math Integrated Math 2 textbook. It is on quadratic inequalities, and this video is actually a long time coming, so I skipped this video. I skipped this section the first time going through IM2 stuff. I apologize for anyone who's been trying to find this section. I'm finally recording it and uploading it. I'm realizing I'm going to have to come across it for my own students, and I'm doing it now. So compared to, I think the last IM2 video I made was somewhere last year, so this is a year later. And this is actually a few months after having not made a recording for a while. I've been on a hiatus for a while. So my only few warnings are, I have been coming off a bad cough the last couple months. I apologize if I have to clear my throat here and there. And also, I may be very rusty, not just in, maybe even in the math stuff, but also just in like my ability to maneuver this stuff here and make sure I'm doing everything right. Every so often, I might have to pause my own video and make sure I'm doing things correctly. Anyway, I'm going to make sure that I get everything uploaded for you guys, like in the description section down below, including timestamps and the description and the playlist and everything like that. So jump down there if you want to find anything. Otherwise, we're going to jump to the lecture portion, and then we're going to do up to problem number 53, if I recall correctly. So without further ado, let's see if I do the first shortcut correctly. Yes, I did. Let's go ahead and get started and talk about this. We're going to graph quadratic inequalities in two variables and solve them in one variable. Now, solving can be by graphing or it can be algebraic, and I'm assuming that the notes is going to show both of them, like examples. They're going to show both of them. And those are our core vocabulary words, and we just have to know how inequalities work in general. Specifically with shading, specifically with shading and that concept of it. Okay, a quadratic inequality in two variables can be written in one of the following forms here. So you notice y is by itself. I might just say y equals by accident, like the idea of just saying standard form, y equals ax squared plus bx plus c, so I'm covering all of them in one, but we're going to use inequalities in their place. The graph of any such inequality consists of all the solutions of the inequality. So we're going to be doing some sort of shading practice with that when we do. You can even see an example down below that it shows. So to graph it, here's what we do. Step one, graph it like this, y equals. Treat it like that to draw what I'm going to call your boundary curve. I don't think they're saying that here, but I'm going to be saying that out loud. So your boundary curve is that curve, that threshold of the parabola, the y equals, that differentiates between what makes your solutions and what are your solutions, what are not your solutions, basically. Now they ask you to test a point. I'm less likely to do that. However, I will be showing you test. I'm going to probably specifically do a lot of testing 0, 0, assuming that your graph is not on the origin. Excuse me, assuming your boundary curve's not on the origin. It's the easiest test to do, really. You compare 0 to just your constant. And if it makes a true statement, that means anything on that side will be true. I kind of want to use this example to talk about it. I will in a second. And anything that's not on that side will also not be true. So if 0, 0 is true, I'm going to shade on the side that has 0, 0. If it's not true, I won't. What I'm going to do instead, though, if it's y by itself like this each time, if y is less than, y'all, I get to shade under the parabola. And if y is greater than, I get to shade over or above. Now, you might be asking whether that's shading inside or outside the parabola. That's not what we're answering. We're answering whether shading under, this is shading under, or shading over. It depends on if the parabola is facing right side up or upside down as well. And then they talk about the shading that represents the solutions, okay? Okay, so here's their example graphing this. Now, they're not showing anything on how they're doing the graph anymore. I'm going to be pretty quick on that. Either if it's in standard form, I'll use negative b over 2, that kind of stuff. I'm going to get the graph and the boundary curve pretty quick. Now it's all about the shading portion. So they're graphing it. All right, they drew this. Now, what we didn't mention yet is the dotted line versus the solid line. This is a dotted line because this is strictly less than, it is not also equal to. So we would do a dotted line for the less than or greater than exclusively. I believe they said dotted line. I think I saw that phrase somewhere. Dashed. I'm sorry. They said dashed line. So dashed line or dotted line. Those are the same phrase. And solid line. Sorry about this. Solid line if it's also equal to. Whenever we graph a y equals equation, it's a solid line. So greater than or equal to, less than or equal to will also be a solid line. It means points on the line are also solutions to your inequality. So they graph this thing. However they chose to. Now, they tested the point 0, -3. I'm not always going to test a point inside the parabola, whatever. But they're testing 0, -3, and they make a true statement out of it. It's kind of tricky because they have a red check. But because it makes a true statement, that means that this point represents a solution to your inequality. That means anything on this side of the boundary curve will also represent a solution to your inequality. So will -1, -6. So will -2, -2. So will 1, -9. 0, 0 would not. That would make a false statement, right? But these would make true statements, so we do the shading to represent that. Now, this also said y is less than. So the way I'm going to see it more so, I'm going to do this a lot more. I'm just going to shade under that curve. Less than, under. When y is less than, you shade under. Okay, and there's the answer to that one. They're going straight to a word problem next. Let's see what they want to say. A manila rope used for rappelling down a cliff can safely support a weight in pounds, provided that the weight is less than or equal to 1,480 times the diameter, the square of the diameter of the rope. So they said graph the inequality and interpret the solution. I always like word problems with inequality things, specifically systems of inequalities. They're, especially for linear things, they're kind of fun. We get to actually see this multitude of solutions that you can have in context of something. So for one, they're really sticking to the first quadrant only. We don't care about negative weight, negative diameters. We probably even don't really care about 0 of either, but 0 of one means 0 of the other. Oh, yeah, they say for non-negative values. Perfect. The less than or equal to means that it will be a solid line, and we are going to be shading under. They say test a point, but it will mean shading under. Here's a basic problem. The vertex is at the origin. It's going to do its stretch thing. Maybe we can use a graphing calculator to hit some specific points, but that's your stretch factor. All right, 1480. So that's fantastic. At 1, 1480. You know, that's a point on here. Anyway, so shading underneath represents solutions to this thing. That means if the diameter is some certain length, then you can maintain that weight there as you're rappelling down, and you'll be good. You can keep that weight. If I chose 1 diameter of rope and 3,000 pounds of weight, what were we using it for? Rappelling down a cliff? I don't know what 3,000 pounds is about. Maybe just because you're so much... I don't know why it would be 3,000, but 3,000 pounds would not satisfy 1 diameter of rope, right? 3,000 would satisfy for maybe for 2 inches diameter, but not 1 inch diameter. Graphing a system of quadratic inequalities is similar to graphing a system of linear inequalities. You graph each inequality and then you identify the region common to them. That's what I will call the overlapping shaded region. So right here, these two graphs, here's the example. They graph this one here. This must be the one in red right there. And then the one in blue, I can tell by the solid line, by the underneath, and the fact that that would be the vertex. This is their overlapping shaded region right here, which does include the point, say, 0, 0. Oh, they said identify the purple region. Let me do it as purple. This is my first time looking at these notes. I haven't recorded something in a long time. I forget. I don't preview things. Yeah, see, they even tested 0, 0. You can see how 0, 0 is a really nice test to use, because what's going to happen in standard form is these will just wipe out. You're just going to be left with -3 on that side and 0 on this side. And same with this will wipe out, and 0 and 3. So anyway, 0, 0 represents a solution to both inequalities. That means it's a solution of the system. So is anything inside the overlapping shaded region. That would include the solid line, the solid curve that bounds it, right there. And it would not include the dotted line at all, including the part that bounds it. So the region itself plus the solid line that bounds it. Any of those would represent solutions to the system. Okay, now that's how the system of inequalities is going to work. So we're just going to graph the two things and figure out where they're shaded together. Now, I went very fast on their graphing and shading. I didn't really talk about it, but shading below this upside down one and shading above the right side up one is where the shading went. Solid line for the equal to, dotted line for the not also equal to. Solving quadratic inequalities in one variable. This is where y is essentially gone from it. Now, we can do a solving by graphing, and I'm sure they're going to have us do it in a bit. But we're going to first talk about solving these algebraically. Excuse me. Quadratic inequality in one variable can be written in any of the following forms here. It's just changing the inequality itself, but they're in standard form. They're going to do a lot of standard form here, it looks like. Now notice they have it set equal, well, against 0, which means if it's not to begin with, you might want to do that. So let's make sure that we do. So to solve algebraically, they're going to be doing, see, they're saying you can solve using algebraic or graphing methods. So starting with algebraically, I imagine they're going to let us be able to factor a lot of these. That's not always true. Definitely not always true. But solving this, what they first want to do, just like graphing, is let's change this thing to an equal sign. The reason before was to draw the boundary curve to create the threshold. This time we're going to set the equals to create boundary value. Oh, they call them critical values. These critical values are what are your x-intercepts of your graph. And when we're trying to figure out when this thing is less than 0, I know there's no y in the picture, and I know we're not showing the graphing first, but it's about finding the values that make these negative, that would make your y values negative, that if this was a right side up parabola, and it is, would go underneath the x-axis. Without us graphing it, just that idea. And these critical values being the x-intercepts are where we go on a parabola from positive to, say, negative. So that those boundary values would give you 0. In between them, maybe less than 0, it may be more than 0. And if we understand the graph, we should know the answer, actually. But we're going to test values. We're going to use a sign chart. And again, I'm saying phrases that they might not actually say. This is me saying them. But if they factor and solve this, they get 4 and -1. Those will go on here. And the way that I'm going to do it when I draw them, guys, I'm just going to have, like, what are they? -1 and 4. And I'm going to test a value in between -4, such as 0, which they're doing as well. We'll test 0 and see if it gives us a positive or negative value. 0, plugging in 0 gives us a negative value here. And that means that it's negative in this case, which means those are values that will be less than 0 here. Anything between -1 and 4 will satisfy it. These would be open circles, by the way, because on -1 and 4 don't count. If you test something greater than 4, such as 5, which they did, they plug it in, they get 6. 6 is a positive number. That's not less than 0. And they try a number like -2 to the left of -1 over here. They also got a positive number out of 6, which is also not less than 0. So only between -1 and 4, exclusive, right, not including -1 and 4, will you actually get values out that will be less than 0 by plugging those in for x. That might have been confusing. That was the one example there. We're going to do a lot more within the problem set if you want to take a look at that time. I think it makes more sense looking at it on a visual level with the graphs. Not that I'm saying we should always solve by graphing. I'm saying that graphing thing will help understand the teaching of what it is that we actually did here. So I think we get solved by graphing here in just a moment. Yeah, right here. So solving by graphing. Let me move myself over here. Solving by graphing. So they give you this one here. Now, that's not a fun thing to graph. I'm going to say that straight up. That's kind of mean as far as the graph goes. In fact, it's even worse by saying they don't even have rational solutions. Look at them using the quadratic, which I would use as well. I don't know, for some reason the plus or minus doesn't show up here. Look at them using the quadratic formula to figure out what your x-intercepts are. So we can kind of answer some of the questions. But we have this graph, okay? It's not a pretty graph by vertex and stuff, but it's a graph. So we have this graph here. And these are the, what color should I use? In this yellow or orange kind of, these are the values of y. I mean, we're graphing it as if it's a y equals equation. These are the values for y that are less than 0, right? They're below the x-axis. These are negative y values. These in green are y values that are greater than 0, right? They're above the x-axis. We're interested in, for this graph, for y equals this expression, and this expression being greater than or equal to 0, we're interested in the y values that are greater than, that are above the x-axis. So we have to figure out where they cross the x-axis. That's what this quadratic formula thing here is for. Now, we're going to have to use a calculator to approximate their values, and they do here. These are the x-intercepts. You can be these x-intercepts specifically and still satisfy this inequality because equal to is allowed. See, if this were equal to 0, the x-intercepts would be the answer, straight up, point blank, end of story. That would be it, this one, and you're done. But what other x values could I plug into here that would also give me values that are greater than 0? The graph is visually telling you that ones that are above the x-axis would be true. Now remember, this graph goes forever. It goes forever up, but it also goes forever left and forever right. So why do they draw these arrows here? Because these are x values that I can plug into my inequality. and I will get a positive value on this side, which means it will be greater than 0. It would satisfy it. Values between negative 1.14 and between 1.47, they would be negative. Those are not greater than or equal to 0. Those would not work. So your two sets of solutions here are less than or equal to negative 1.4, or, and that's a big word, greater than or equal to 1.47, provided that it's above. Now, I don't know if I needed to draw the graph per se to know that answer. That's why I wanted to bring it up on this one here. This is a right side up, not that we're supposed to solve this by graphing, but we could imagine it. This is a right side up graph. If a right side up graph crosses the x-axis here and here, then I know to the left of it and to the right of the x-axis, to the right of my intercepts, to the left and right of my intercepts will be the positive values. In between them would be the negative values. I know that because it's a right side up graph. Right, it's a positive 1x squared. And that's what I was saying by the visual to make sense of that's why these would be positive. Oh, you wanted negative here, and these would be negative. I'm very, very rusty at this, guys, in teaching and stuff. It's been a long time since I've done this, so I apologize if I'm slow, if I'm belaboring, or if I'm too chatty, too rushed, too much of like, oh, this is what I want to say. Specifically, like I'm saying the words boundary values instead of critical values, or boundary curve. I forgot what else I'm saying. But yeah, I want to make sense of it my way that I'm going to teach it and do the problems. Hopefully this last example. Modeling with mathematics. Okay, a rectangular parking lot must have a perimeter of 440 feet and an area of at least 8,000 square feet. So we have a perimeter formula here. So perimeter equals... Wait. Oh. It says must have a perimeter of 440. I thought it said it must at least. But the area is at least 8,000. So length times width must be at least 8,000. The 2 lengths plus 2 widths must be 440. Okay. So what they're going to have you do is, this is a system. We're going to take this equation, solve for a variable. Their choice is solving for w. Replacing this expression for w in the inequality right here so that you can construct a one variable quadratic inequality, such as this, length times width, but here's your expression for width. They distribute to create a quadratic. They subtract 8,000 on this side to set it against 0. Now, personally, I don't like negative a values so much, but you know what? It looks like they're using the graphing calculator, so it's whatever. That's okay. So we're finding the L-intercepts here to see what satisfies. We're trying to figure out the possible lengths of the parking lot. We need to make sure that this expression is greater than or equal to 0 at all times. It looks like it can be equal to as well. Not L, but the L that I plug in to this can, make something here. So, we're using the graphing calculator. We use the 0 values. I'll make sure that my graphing calculator is up and ready to go for this kind of thing. And you can find the two intercepts. These represent L. You can have lengths of about 46, they said 49.7, what is this, feet, you have 45.97 feet and about 174.03 feet. If the length is anywhere between those two, then you're good for having that stuff. I don't know, it says describe the possible lengths, and I think that would be it. They're having you explore some things as well if you'd like to by trying to plug a number that's in between and see if it actually works out, and it should work out. Okay, I'm going to leave it there. Is that it? Yeah, that's it. Okay, awesome. All right, guys, we're going to do the vocabulary and core concept check. They have 2 questions we got to answer here. Number 1, compare the graph of a quadratic inequality in 1 variable to the graph of a quadratic inequality in 2 variables. Well, I was thinking of a system. A 2-variable one uses both x, y. It's x, y axes, but the 1-variable ones, if you remember, like solving algebraically, I guess you can still graph that way, but I think they're talking about the number line graph. So the one variable is a number line. Okay, it's just one-dimensional, and 2-variable is, this isn't any different from equations, I guess. 2-variable is a x, y axes, like the whole coordinate plane. So I'm just going to keep it short. Number 2, explain how to solve this using algebraic methods and using graphs. I don't know if they want us to actually solve it. That's kind of set for these problems down below. But to just explain it, it looks factorable. So set equal to algebraic. Let's keep these kind of short. Algebraic, we set these equal to 0. We set this equal to 0. Equal to 0. And solve by factoring. Find the critical values by factoring. So that's like zero product property. So I'll put ZPP. Then use a sign chart to test values against left and right of the critical values. Of the critical values to find solutions. Sorry about that. That's doing it that way. That's algebraic. Let's do it via graphing. Graphing, set y equal to expression. Then find the values. Oh, sorry. I'm typing more about finding the solutions later. Then find the values that are below the x-axis. Values of x that provide y values points below the x-axis. Okay, now for this one, use a sign chart to test values left and right of the critical values to find solutions that are less than 0. Negative solutions, that's all I wanted. Because this is specific to this actual inequality, and that one says a negative. Okay. Kind of a lot to type. It's more to type than I normally would for those ones there, so I hope that's pretty good. Okay, guys, I am set to do problems 3 through 53. If you are as well, you would probably want graph paper for some of these, so I'm probably going to provide I'm looking right now. I have the tall graph paper for quadratics. I'm probably going to be using those ones, so I'll provide in the PDF down below. Graph paper, printable graph paper there, 6 graphs on each side. They won't be scaled with numbers. They will have little increments and such on them, though, when we're ready to go. So I'm going to go ahead and get started here. We do numbers 3 through 6 to begin with. Okay, numbers 3 to 6, match the inequality with its graph. Explain your reasoning. So I'm just going to go ahead and write down the inequality itself. And then I'm going to write the letter that associates with it. Now, what I'm looking for is a couple things. Well, for one, these C and D have the same boundary curve. A and B have this. Oh, no, they don't. C and D have the same boundary curve. They're both upright facing graphs, so is B. But what I see in particular, regardless of boundary curve, is 2 of them are shaded below B and C. 2 of them are shaded above A and D. Now, they didn't talk about shading above versus below the boundary curve. I did in my lecture portion. If y is isolated and y is greater than, you'd be shading above. If y is less than when it's isolated, you're shading below. This equal to also represents a solid line. So I'm looking for a solid line that rules out A and B. So it's either C or D, and I'm looking for shading below. It's going to be C. This answer is going to be C because solid line, solid curve, boundary curve, and shading below. Let me do this again. If you skipped my intro, guys, I haven't recorded a video in months. I'm talking like 5 months, 6 months, 6 months, something like 4 months. I haven't recorded a video in a long time. I'm really rusty with the handwriting and the temperature in my room and stuff like that. Number 4, y is greater than negative x squared plus 4x minus 3. Now, if there's one giveaway for this, it's that this has a negative stretch factor. That means the boundary curve will be upside down. The only one that is upside down in this is A. So I already know the answer is going to be A, just by process of elimination. If we're going to talk more on reasoning, we can talk about this having a dotted boundary curve and shading above as y is greater than. So dotted curve, shade above. These are things I'm going to be doing when I sketch my own graphs. Probably number 7 onward is graph the inequality. Yeah, starting number 7, I'm be doing that. Now, we have to draw the boundary curve, and I'm probably going to go pretty quickly with that. Chapters 3 and 4, especially chapter 3, taught you guys anything about how I graph quickly. This is the last vestige of us being able to do that, and I intend to do it as fast as I can. So what have we answered? C and A? All right, number 5 is between B and D, and 1 has a dotted line, which should represent number 5, and I also shade below, so that sounds like a good answer for B. Dotted curve, shade below, and then number 6 must be D. Now, among the other things that make it D, one of them I want to mention is that D has actually the same expression as number 6 has the same expression as number 3, which means it'll have the same boundary curve. Remember when I mentioned that C and D have the same boundary curve? So they match as far as boundary curves go, right? They're the same, just different shading. This time this is greater than or equal to instead of less than or equal to. We're shading above the curve, which happens to be inside of it this time. Solid curve. Oh my gosh. Solid curve, shade above. The fact that I haven't written anything in a while is kind of scary. Ugh, okay, sorry about that. All right, numbers 7 through 14, graph the inequality. Now this is where I got to pull these things out right here. Let me get it ready. Copy, paste. All right, this is where I'm going to pull these things out right here for the graphing, all right? Number 7, y is less than negative x squared. Like I said, I'm going to be pretty fast with the graphing of this, and I hope that's okay. And this is going to be kind of a waste of space. But what I'm going to do here is draw the boundary curve. Now, negative x squared is just the flipped over version of the parent function. We go 1, 1, 2, 4, 3, 9, 4, 16, downward from here. Hopefully you know what I mean if you've been following my videos with graphing. And this is less than, in that it's not less than or equal to. So my boundary curve will be dotted, not solid. What you could do is you could draw the curve and then use like an eraser to get rid of the marks afterward. I don't know which would be faster for me. This is probably fine. Ooh, little rough. And then the less than instead of greater than means I'll be shading below this curve, not above it. So below is inside in this case here. Some of this stuff will get a little strange when it comes to, watch what happens when I let go here. Okay, that was fine. That kind of snapped in place. Now, generally, what the book talked about was testing a point, and I talked about testing 0, 0. That actually doesn't work for this question, or for number 8 for that matter, because 0, 0 is on the boundary curve. So I'd want to test a point that's either below or above to see if it works. I know the book did 0, negative 3 at one point, so let's try it and just see what it does. Your teacher might be asking about that. And in fact, you can get test questions to ask, is 0, negative 3 a solution to this? And you want to know what that means. So I'm good at helping you there. So let's see. Is negative 3 less than negative 0 squared? Well, negative 0 squared is negative 0, which is 0. Is negative 3 less than 0? Absolutely it is. So what that means is that it's a solution to it, and everything else on this side of the boundary curve will also be a solution to it. That's what the shading's representing. See, people might not know why they're shading. Like, I'm just coloring things in, right? The shading means this point works, and this point works, and this point works, and this point works, and this point. Instead of freckling this with a bunch of points that you can't fit them all, we do that. That's the same reason that we draw lines and curves with arrows and stuff, because instead of drawing a bunch of points that represent them, there's that. Now, the dotted curve is just our visual representation of telling somebody that a point on the curve is not a solution. It's not that they're actually broken line parts. This is a full barrier, but points on it don't count. Just like when we do open circles to represent points that don't count on a number line, and you're going to see those later. Okay, number 8. Y is greater than or equal to 4x squared. Once again, this is a one whose vertex is on the origin. I haven't even spoken this much in a while. Y is greater than or equal to 4x squared. Its vertex is on the origin. It's got a stretch factor of 4. So over 1 up 4, over 2 up 16. 4 times 4. It's going to be very, very sharp. This will be solid because it's also equal to. These are the hardest curves for me to draw, so I apologize, it's not perfect. And it's also greater than, which means we will be shading above this thing, which means it is within the curve itself. That's actually not bad. Draw your arrows. Sketch your curve. I'm going to try and do... that won't work very well. Pardon me while I go for this. Ooh, that lays on pretty thick there. My bad, y'all. Pretend like that's just shaded within, okay? You're good with that? All right. Watch when I test 0, -3 this time. I don't expect a true statement to come out, right? Only things inside the shaded region, which, if I did this well, would actually look more like... Oh, boy. I can't really erase it. When I test 0, -3 this time, I get 0... Whoopsie. I get -3 is greater than or equal to 4 times 0 squared. You're going to start getting used to the fact that plugging in 0 for x will just give you a 0. So I might have to do that. Is -3 greater than 0 or is it equal to 0? No. That didn't mean I did anything wrong. That actually means I did it right. On this side of the boundary curve, anywhere, anything here will not be a solution. Only inside, only above the boundary curve will be solutions. That's what the shaded region is all for, and that's what testing that kind of shows. I think the book was talking about testing inside the curve each time, and so you'll get some true statements, you'll get some false statements, you'll see them. I'm going to be about shading above and below. I hope that's okay. Like, kind of here on out, I might do that more so. I might want to show some 0, 0s because it's easy to show the test. I'm not really calculating anything. So I hope you're good with that. All right, number 9 looks like this guy here. So the graph, this has a vertex at 0, -9, right? The y-intercept is also the vertex of this one. This has a traditional 1, 1, 2, 4, 3, 9 kind of setup. So I'll graph what I can. 4, 16. 16 up from -9 is 7. And 25 up should fit. 25 up from -9 is 16. So that does fit here as well. I try and plot what I can fit on these tall graphs. We will have a dotted line. Y'all. And the greater than means we should be shading above. So let me get this one done here. You can do it as well. If I test 0, 0, you can tell that 0, 0 is inside the curve. Well, it doesn't matter for being inside the curve. It's above the curve, and therefore will be inside the shaded. It'll be a part of the shaded region, which means testing 0, 0 should represent a solution to this thing. So as I shade within here, there we are. So I shade within there. That'll represent my solution set. So my test is 0, 0, maybe one of my last ones, or my first of 0, 0. Straight up, I plug in 0 for y and x. You can see all that will be left is the constant to test against. Y'all, is 0 greater than -9? Yes. I'm on the right side of the curve when it comes to shading because it's inside my solution set. So that's what I'm trying to get out of that. All right, number 10. As you can tell, there's going to be a lot of graphing going on here. If you've seen it in my old videos, as I recall, I kind of painstakingly go, not again. You probably don't have to graph as many as I do. So number 10, x squared plus 5. This time, we got our vertex. It's still on the y-axis, 0, 5, like that. Oops, I want to make it blue. But we are going upward, so less points to plot. 3, 9, 14, like that. Less points to plot. I'll be shading underneath. Now, I think this is the first one that I'm doing, although we saw it on the numbers 3 through 6. This is the first one that I'm doing where the shading is outside of the curve because it's underneath the curve. So, sorry, as I get the setup. So my shading is going to be on the outside here. This kind of takes a while too. Sorry if I get kind of like whatever with it. Blobby and messy. I want to kind of fill it in. But I seem to recall this being kind of a nuisance. It's really bad for my stylist to be doing this. So I might kind of, I don't know. For now I'll do it. But it's bad for the pen tip. Did I order more pen? I gotta remember if I ordered more pen tips. They'll be lying around somewhere if I did. Anyway, I think I did. I think this is one of the new ones. Anyway, so that would be it. 0, 0 should work, right? It would say 0 is less than 5. That's a true statement. And there is the graph for number 10. Now, you might not be using the graphs that I am, and probably better off if so, because these are very tall. I intend on using these when they start using, like, I don't know, maybe they won't have really weird graphs like I have here. All right, y is less than or equal to x squared plus 5x. Now, this is one of the ones I'm not as fanciful in wanting to graph for a couple reasons. We're going to talk factoring later, you know, the whole factoring thing. And so this factors into, this factors into x times x plus 5. I'll still say less than or equal to like that. Just so we can talk on intercepts. Intercepts are 0 and -5, if I wanted to just treat it that way. And then the axis of symmetry is halfway in between. Now that's at -2.5. The goal of this section is not teaching you how to graph these, though, right? So this isn't going to be a long explanation on how I'm graphing it there. And I got to plug -2.5 into here to figure out what the y value is. Not less than. We're actually literally doing it this way. 2.5. Sorry, positive 2.5, and that's 6.25. Okay, so this is my vertex. Right there. Oh, excuse me. -6.25. This is my vertex down here. And I'll go 1, 1, 2, 4, 2, 3, 4, 3, 9. Oh, I'm not going to do this very well. Hold on. I think it's right here. 4, 16. 10, 11, 12, 13. I don't think I can fit 525, so I'm just going to do that. Solid line, also equal to. So solid line for this guy. Now I could have used -b over 2a. That would have gotten me straight to, you know, that wouldn't have gotten my intercepts. I was kind of a fan of getting some points as intercepts to kind of get something in there. That would have just gotten my -2.5 value. So I wanted to do some factoring, plus we're going to factor later. Y is less than or equal to, so we are going to be shading below. Once again, also outside of the curve. Now, it's probably in our best interest, that means mine as well, to keep extending this, because if we're talking about doing below, I want to do below any part of the window range that I'm including. Which means that little part right there. So below will look like that. Here and here. 0, 0 would not be, where's 0, 0? Oh, 0, 0 is on the boundary curve. So 0, 0 is not one to test. I'm not going to test anything right now. Okay, number 12. Oh. They're making me not want to like graphing. I don't even know if that's factorable. It actually might be. So, hold on. -2x squared plus 9x minus 4, minus 4, minus 4. Let me think about that. Factor out the negative. Is that right? -8. Yeah, it's factorable. All right. This thing is factorable, so that therefore I can get my intercepts. I know that's not going to address every part, but this vertex isn't going to be fun. Hopefully you're not given this. I'm not going to give my students this problem. Hopefully you're not given this problem for the thing here. As far as the x-intercepts go, you're going to get 1/2 and 4, which is, 1/2 and 4, which is only like one part of this little battle. Because, oh my gosh. Because the vertex is halfway between these two values. What's halfway between 4 and 1/2? So 4 plus 0.5 divided by 2 is 4.5 over 2, which is 2.25. That is your axis of symmetry. X equals 2.25. 2 1/4. See, that's not 2 1/4. Is your axis of symmetry. That's not even your y value. I'm not getting, there we go. What's more like 2 1/4? I only have 1 of 2 choices. I'll choose this one. The y value, and then forget the 1 1 2 4 stuff is going to be, well, and 2 is your stretch factor. Let's plug in 2.25 into that equation there. 2.25 times 2 is 4.5, minus 1 is 3.5. 2.2, I'm going to use the calculator here. 2.25 minus 4 is negative 1.75, if I did that right. So negative times negative will be positive. 3.5 times 1.75. I mean, you could have 6.125. You could have, again, used the negative b over 2a stuff. It's not going to change the x and y values that you get, and I got extra values by doing the factoring as well. So 6.125 is 6 1/8. Now, from here, I can go over 1 down 2. Is this on? No, it's above it. Over 1 down 2, like that. Like that. Over 2 down 8. 2, 3, 4, 5, 6, 7, 8. About that-ish. That-ish. What's over 2? 1, 2 down. See, this is at the half mark. This is at the quarter mark here. So this is tricky. I'll just do one more if I can fit it. Over 3 down 18. This is 6. This is 6. Negative 12, and just up from the negative 12. Right there. And then probably about right there. Okay, that's best as I can do, y'all. Sorry. All right, solid line, shade above. Solid line, shade above. Oh boy. Solid curve. Solid curve, shade above. Sorry. This is really hard with the stylus, guys. I'm just going to kind of be mucky. Not enjoying that graph. I hope the next couple... 14 looks kind of weird, but at least we already have the vertex. And I can't see. I'm blocked by my calculator on number 13. I have no idea what it looks like. Yeah, greater than, shade above. Okay. My hope is, for the most part, they're not giving us a lot of those. I don't see what the benefit is of practicing something like that. I mean, you can practice any graph, but you're practicing. I mean, you're only 5 problems in to doing it. So, yeah. All right, number 13. Okay, vertex form. So we got a couple vertex form problems. Probably better for us in general. We just use the stretch factor after that. And these numbers are good. So on number 13, I have a vertex at -3, -1. My stretch factor of 2 is over 1 up 2, over 2 up 8, over 3 up 18, which I think hits that top. We will have a dotted boundary curve. We will be shading above. Greater than, this is a problem I'll assign to my kiddos. Greater than, shade above. There we go. Excuse me. I'm trying to find the right thickness for my shading, sorry. So I gotta, oh, close enough. So I gotta fit it in here. I prefer shading inside more. Okay. Number 14, last one of this set. Y is less than or equal to. So solid curve, shade below are already 2 things that I know about it. Now we just got to know how to graph the boundary curve. It's got a stretch factor of 1, goes upward. Now 1/2 is 0.5. So at 0.5 comma, this is 2.5. And it goes upward. So 0.5, remember it's opposite of the sign. 0.5 comma 2.5, smack dab right there. We got a 1, 1, 2, 4, 3, 9, etc. relationship. 2, 3, 4, 5, 6, 7, 8, 9, I don't think 416 can fit. We'll leave it at that. We have a solid curve. We are shading below, which is just too bad. Now, testing 0, 0 here is not as fanciful as before because now you actually have to calculate something. I'll show you what I mean. I should know it should work. I'll show you what I mean by why I know it'll work. But 0, 0, this is no longer standard form. Wait, is this? Okay. This is no longer standard form. So, plugging 0 in for x, yeah, it'll cancel out the x, but it's not x that's just squared and multiplied by coefficients. X is subtracting with 1/2. So you'd have to actually compute that to make something happen. Now, the test, if I want to try 0, 0 regardless, is 0 less than or equal to a positive number? 0 is less than or equal to a positive number, excuse me. When I plug 0 in for x, I will get a positive number. I don't care if I'm adding or subtracting 1/2 here. I'm squaring it. It's going to turn that positive. Plus this number, not every problem is going to work this way, but plus this number here, a positive plus a positive, that's a positive. 0 is less than or equal to positive is true. 0 would work, and it does. And so I trust my graph and stuff. That looks good. Okay, we're done on numbers 7 through 14 where we graphed. Numbers 15 and 16, we are going to use the graph to write an inequality in terms of f of x so that the point P is a solution. Oh, so we make up our own? Okay. I want to make sure... Oh. Yeah. Okay. 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 I might do vertex form to make sure all's good. It looks like the vertex is on... no, here, let me copy paste this over. Looks like the vertex is on the x-axis on number 15. This is kind of a weird... This is, for one, it's an open-ended question. You can create more than one inequality in one thing here. But I think we want some accuracy to this. So for vertex form standards, we need our... this can... Pretend like this is like 3, 0, right? That's me making that up. It could be 20, 0. It could be 1.2, 0. But I'm going to use that. Now... the shading that we're going to have, and I'm not going to do this like full bore, but the shading we're going to have is going to be here. So P is a solution, being greater than it. It's got to be something that exists in the third quadrant, whatever. I don't think I have to do too much to make that part happen. It's a solid line. Y has to be greater than or equal to this thing here. Y is greater than or equal to. And I'm just going to call it x minus 3 quantity squared. That whole flip keep thing, this would be a plus 0 for your y value of your vertex. I don't really need it. That should work out just fine. They didn't say what p value we have, right? So that works. I guess we're good for that thing there. Oh, they said in terms of f of x. Okay, got it. I don't think we had to make up a thing here. I think all we had to do, we probably just had to say this. Y is greater than or equal to f of x. I don't know if that's right or not. I kind of want to make up inequalities to kind of use something out of that, but I guess that works. I think they want you to know whether you're shading above or below. I don't think their goal is for you to create some... Oh, by the way, this would have been negative. I don't think their goal is to have you create one of these. So I'm just going to go ahead and say that. But if I do, number 16 is the same answer. Number 16... It says in terms of f of x. Use the graph to write an inequality in terms of f of x. So point P is a solution. I don't know if I was supposed to do the greater thans or not. I'm not sure. Yikes, I have no idea. Okay, well, you know what? I'll do both anyway. Okay, number 16. Because otherwise number 16 is the same answer as 15. It's a solid line. And we'd be shading above since P is outside of it. So let's go ahead and just make up another vertex. Let's see. This I'll call -6, -4. Okay? So my inequality there, and it's an upside down graph, right? But P is above. You want P to be a solution. It's a solid curve. So Y is greater than or equal to, once again. It's a negative once again. I don't know the stretch factor. I'll make one up. Let's call it 1/2. and x plus 6 quantity squared minus 4. There you go. But it said in terms of f of x. I don't know if that's supposed to be an f of x, or y is greater than or equal to f of x. I don't know the right way they want an answer. They did say in terms of f of x, so at the very least, what I will do is put f of x's right here for these ones. But I'm giving you a couple outlets for what you can put. I just don't know which one they want as the answer. I would believe, almost in a way, that they want these answers here. This one and this one. The only reason why I'm not sure is because it's the same answer. Why didn't they do a dotted line? Why didn't they do one below? I don't know. Let me clear my throat for a second. Hold on. Okay, yeah. With all that excess coughing at the times and not a lot of talking recently, getting some throat issues there. All right. Next exercise is 17. Oh, geez. This is going to keep happening. Next exercise is 17 and 18. Describe and correct the error in graphing these. All right. It's the same graph. Excuse me. It's the same inequality. Two different graphs. Both of them wrong in some way, right? Now, they said correct it. It's going to be the same graph for both. So correcting one will correct the other. I'll put these kind of right next to each other, okay? So number 17, I already saw the issues. I just got to indicate them now. On number 17, they did a dotted line instead of solid line. Curve. Oh, dashed. I think they used the word dashed. Dash curve instead of solid. On number 18, I'll write the 18 in a second. They shaded below instead of above. So 17 is that one. 18 is this one here. We'll correct both. I'm going to use, well, if you're using the same graph paper I am, I'm going to keep up with it. So the boundary curve's right. The x squared plus 2 thing, y equals. That's right. So up we go like this. I'll just go and do that. So we will be shading above, but we need a solid line. So both of them have something right. They have the right boundary curve. One of them is should be dotted or solid instead of dotted. One should be shading above instead of below. It's the best of what's wrong with both of those in fixing it. And that's what it should look like. Not bad. Two answers, two things to answer in one. 17, 18, boom. Number 19, modeling with mathematics. A hardwood shelf in a wooden bookcase can safely support a weight W in pounds provided that the weight is less than or equal to 115 times x squared, where x is the thickness in inches of the shelf. Graph the inequality and interpret the solution. Now, in my mind, sorry about this, I just want to think about this. This has nothing to do with the problem specifically, but there was a lecture problem that was like this. And in my mind, I'm curious if, not just if this is accurate, but the whole squared portion is due to effects of not just pressure, but gravity. Force as the weight increases, whatever the pounds per square inch something are really important in that way. That might be the case. Anyway, what do we want? So W is less than or equal to 115x squared. If you were or weren't in tune with us for the lecture portion, the important thing here, guys, is we're just looking at the first quadrant, right? We don't care about negative weights, negative inches, lengths, anything like that, just first quadrant stuff. So here's x, here's w. Now 115x squared, we go over 1, we go up 115. I want to make sure you recognize that. So I'm going to go pretty I want to do like a 1, 1, 2, 4 kind of thing. But that 2 and that 4, or that 1 and that 4 over here, this is 115. What's after that? 230? Hold on. 440, no, 345. What am I, nuts? 345 and 460. Okay. So we're going to hit here. Oh, this is 1, by the way. And this is 2. And somewhere in between there are 0.5s and things like that. But here's my 1, 1, or 115. And 2, 4, 4 times 115 like that. And the graph is just doing this. So there's my sketch. Maybe we could have used a graphing calculator, but there's sketch. Now, less than or equal to is shading underneath this curve. Okay, so we are underneath. I'm going to go kind of thick. I'm going to lay it on thick to start, and then when I can't fit it, I'm going to do a little bit of that. So the only problem with using that, so what I'm doing here in this blue, this isn't a different color. This is a lesser opacity. Problem is, when I draw again, because I'm going to do, just kind of fit it inside there, you're going to see this. There's going to be a little bit of overlap. When I hit right here, see how it gets darker right there? The opacity kind of increases. Okay, graph the inequality and interpret the solution. Okay. By interpreting the solution, I believe they want us to choose a point and talk about what can work and what can't work. Okay, so if my curve is accurate enough, we already sketched the graph. If my curve is accurate enough, I'm guessing, this should be true for linearity's sake, non-linearity's sake, I'm guessing that at 1.5 comma 230, that'll support that weight. So a bookshelf, a hardwood shelf with a thickness of 1.5 inches will support 230 pounds of weight. Anything that's in this shaded area plus the solid curve will be supporting that weight. And 1.5, halfway between 1 and 2, all that should be within that range. Okay, number 20. A wire rope can safely, well, it's the same kind of question. It's just a different one. So a wire rope can safely support a weight in pounds provided this, sketch the graph and interpret the solution. So a lot like the previous one, let's do the same stuff. Let's write it out. Hold on. All right, W is less than or equal to 8,000 d squared. I didn't really read the context. I'll do that afterward. Let's get the drawing first, shall we? Lay it on a little thick there, buddy. All right. D, I think, was diameter or something like that. 8,000 d squared. Look, I'm not going to do anything different when it comes to the idea of the graph. This is still a 1, 1, 2, 4 thing to me, but my 1 and my 4 for these things aren't exactly 1 and 4, you know what I mean? 8,000 is the stretch factor, so 8,000, 16,000, and I'm probably going to do the same things I did last time. 24,000 and 32,000. I can say that 1.5 stuff. I might use another number, but that one looks a little closer to the 2 than 0. All right, we hit 0, 0. We hit 1, 8,000. We hit 2, comma 32,000. Maybe we can interpret this time something that's not a solution, that does not work for this. I got to see what the question or what the context is again. But it is, once again, a solid line. It is, once again, shading below. Honestly, I could have just copied and pasted my other graph and just changed the numbers on the y-axis, the w-axis there, and changed the x to a d. Same idea. If you did both problems, same idea. If you're learning, try it for yourself. See what you get there. Okay. Interpret this guy. A wire rope can support a weight provided this, where d is the diameter and inches the rope. Let's choose something that doesn't work. Let's choose 1, comma 24,000. This will not work. A wire, a 1-inch diameter wire will not support 24,000 pounds of weight. That's kind of the interpretation there. I mean, that's one example, but that's the idea. This is an infinite number of solutions. That's what the shading's all about. We can't address all of them. If we do, that's what the graph is about. That's what the inequality statement's about. We can't say them all. That's what these representations are for. That's why we solve them this way. That's the idea behind it. Okay, we're going to do some systems of inequalities on numbers 21 to 26. The reason I might like these ones slightly more after a couple of them is because I only concern myself with the overlapping shaded region when all said and done, but it's 2 graphs in one, and I'm sure they're going to muck us up with some really foul ones. I'm looking at number 24 and not liking what I'm seeing already on one of them. All right, number 21. Y is greater than or equal to 2x squared. Y is less than negative x squared plus 1. For consistency's sake, I'm going to try and do these the same each time. I'll use blue. I'll use red. The overlapping shaded region will be purple. Sound good? All right, let's go ahead and graph both of these things here. This actually will probably take longer than I first said, saying, oh, this will be fun. I suddenly don't think so. So the 2x squared, it's two problems in one from before. So stretch factor 2, vertex at 0, 0, right? And now we're going up 18, over 3 up 18 there. Solid line, solid curve, shade above. Solid curve, shade above. Yeah, you know what? I take it back. This is going to take pretty long. Bear with me. You'll be with me here for a while if you're doing all of them. Or if you're watching all of them. All right. So in blue is this guy here. Now, these are not solutions. These are solutions to the single inequality, not to the system. Right? To solve the system. I'm getting hot. To solve the system, we have to find the overlapping shaded region. Negative x squared plus 1. That's going to be starting here. This is a very small, guys, this is a very small overlapping shaded region. This goes downward, yes. This one's going to be hard to even show the overlapping shaded region on this guy. I didn't know. Okay, this is a dotted boundary curve. Hopefully you can see this red okay. Sorry if it's a little bouncy, is the way that I describe it. Maybe I can use a different color red. And shading below here. Now the overlapping shaded region is the solution to the system. So these two only overlap in that very, very, very small space right there. All this drawing that I just did right here means very little. This, what I'm filling in right there, and I know that's hard to tell because it kind of just looks like a black blob. I'm making it purple. Let's do a more transparent version. But that is the overlapping shaded region right there, guys. That's the solution to the system. Nothing in exclusive blue or red are solutions. Just that little guy right there. It's hard to even test points. Like 0,5 is among the... It's an infinite set. It's just a small space, small area to work off of there. But that's it. All right, hopefully we get better results from some of these other ones. Number 22, y is greater than negative 5x squared. And y is greater than 3x squared minus 2. Interesting that they're both going to be shading above, right? But one's an upside down and one's a right side up here. So negative 5x squared is at the origin for the vertex. This will be in blue. I can't even do the over 2. Over 2 is down 20. This is 17. It's negative 17 right here. So like 18, 19, 20. I'm just giving it the idea so I don't go fully vertical here. These will be dotted. Both of them will be dotted, in fact. And both of them are shading above. So this guy is looking like this. And that is a curve. It's a lot to shade above with, too. I don't know how to do this any faster. The thickest I can make it is this guy here. You know what? I'm not going to use my stylus. I'm going to use my mouse. I don't know why I didn't do that before. Hold on. I know why. This thing's in the way. It's probably not going to be super accurate, but... Yes, that is much better for my stylus tip to use my mouse instead. At least for these big ones like that. Remember, this is not the solution to the system, just to the single inequality, which is a lot. They're all infinite. They're all a lot. Y is greater than 3x squared minus 2. Ooh, this is still a small space. Okay, so this vertex is at 0, negative 2. Goes over 1 up 3. Over 2 up 12. That's all I can really fit. It is a dotted line with shade above. Once again, a very, very small, guys, overlapping shaded region. Oh, no, I take it back. It's not very small at all. I was thinking it was within the two curves. It's not. It's not at all. But we do have to talk about what it is and what it isn't, because my last curve was a little messy in drawing there. My bad. I'm going to try to use my mouse again and see how this goes. Okay. The problem is the way that I kind of drew the blue in that one small space, and I got to see if I can kind of delete some of it. Okay, guys, so here's what's up with this one. We're talking overlapping shaded region, right? Now, what's unintentionally there is that guy right there. That is not supposed to be overlapping shaded region. That's not supposed to be blue there, so my apologies. The only overlapping shaded region, and I'll try and mark it in as purple as best as possible. The overlapping shaded region is, let's get it thicker. This purple area here, right? The blue and the red together, but not below the blue curve, right? So this area and a bit of, if I were to fit some more in, a bit right here and right there. So not here, right? This should be exclusively red, and these are exclusively blue, but right there is the overlapping shaded region. Very funky looking, my bad, but that should be it. Now, if there were an answer key, it's unlikely that it would actually show the shading of the other parts. What I think I'm going to do here on out is I'm only going to sketch the overlapping shaded region, and it's going to be as simple as shading above or below each curve and just going from there. Above this one, but below this one is this region. That's the best way for me to talk about it. That's what I'm going to start doing. I'll still draw the boundary curves. Number 23. Okay. I have not yet done the negative b over 2a stuff. I still don't want to, as long as I can do factoring, and these look factorable. So this one, that's a perfect square trinomial. Like that. That's actually very close to the one that I made for that one example, like number 15 or something. This one factors to x plus 4 times x minus 2. Okay, now this one is straight up vertex form. This one factored form is going to have a very easy to find vertex. And I got some points with it. So I choose to graph how I'm going to here. This one, let's use red for this. I apologize. I don't know if using red is as fun anymore there. I'm going to get a darker red for y'all. Is that okay? I'm calling that red. All right. You know what? I'm just going to start using green. Now that I'm not going to draw the two things, I tend to use blue and green. Now that I'm not going to draw the two things, I don't care about making it purple. In between is being the overlap. I'm just going to make it purple anyway. All right, so 2, 0, stretch factor of -1. Solid line, solid curve. And we will be shading below it. Now, I'm not going to do the shading right now. I'm going to wait. I'm going to find out where this other curve goes. I'm going to overlap that, or find out where that would be shaded, and I'll talk about the overlap after. But it would have been below. Nothing will be above for this solution set to the inequality. Just keep that in mind. The next one, we are shading below as well, but this is a different curve. So this one, the only things I know about it so far are the intercepts of -4 and 2. See that one? Now, the axis of symmetry is in between at -1. So -1 plus 4 is 3, and then times -3 is -9. So my vertex is at -1, -9. Oh, it's right there. -1, -9, 1, 1. Oh, y-intercept of -8. That tracks. 2, 4. 3, 9. Hey. 4, 16. 7, and 5, 25. Which I think is there. 25. Okay. Dotted line shade below. Now, what is below, or dotted curve, shade below. Now, what is below both this curve and that curve, right? We want the overlap. Normally, and this is actually probably harder than I'm making it out to be. Conventionally, we like to see overlapping shaded region to just be the in-between, above one, below the other. But this is below both. So what's below the green curve, yet also below the blue curve? It's going to be this region here. It's going to be this guy. I got to stick below both. Right? I got to fit a little bit more. I just got to make it less thick. So fit some right there as well. This is the overlapping shaded region of both for that particular one there. So that's what that'll look like, right? So I'm just going to do it that way. And I don't know how the book talked about or would talk about things. I don't know if they're testing points each time still. That's a little too much for me to be doing, so I ain't. I was all about 24 maybe being bad. At least that second one is still factorable, but if the vertex is bad, then it's just harder to draw. So number 24, that top one should be fine. Bottom one, not so much. That's an X. All right. So x squared minus 4 for the top one, I'm doing in blue. It's got a vertex right there and a stretch factor of 1. So let me kind of just get that on. Negative 4, right? So up 9 and 16. Okay. Solid line we will be shading above. Ultimately. Okay. We're at number 24. We're not even halfway through. I mean, all depending on the graphs, right? We will be shading above. We're below this next one. Does look factorable because that last one that we did, I think so. Because that other one that we did that was like this, but not exactly. I just see the numbers in my head and I'm going for it. So minus 4 plus 1. Negative 8 plus 1 is negative 7. Okay, so there's that. So, okay, so this looks kind of like that other one here. It's got x-intercepts. This time negative 1/2 instead of positive 1/2. So I don't think this graph will be very fun to do. That's a 4, by the way. So a 4 and a negative 1/2 like that. The axis of symmetry is halfway in between those ones. So 4 minus 0.5 over 2 is 3.5 over 2, which is 1.75, which is the axis of symmetry right there. I really kind of want to draw it, but very faintly. So 1.75, looking probably like that. I hope you can kind of see it. Now I got to plug in 1.75 into something to figure that out. Let's do the kind of the bottom equation there. So negative, and then to 3.5 plus 4.5 times 1.7 is a negative 2.25. Help me out, calculator. $10.125 positive. Whoops, 10.125, and this will go upside down, which totally makes sense. It'll be a solid curve. We'll be shading below. So 10.125 way up here. That's 10 and an eighth. And now we got to do some of this stuff. So pardon me here. Over 1 down 2. Over 2 down 8. I got to go over here though. This is kind of hard. and then it hits those intercepts, right? So it's kind of, I like to do that to kind of confirm I'm doing that part right. And the y-intercept should be 4. So that, it actually even hits these points here. So that, oh, that didn't reflect right. Hold on. 1.75 over 3.5 over, got it. So it hits this point and then this point like that. Okay. That's actually not linear. Over 3, I'm going to fit one more. Over 3 down 18. 18 down from 10 is negative 8, but 1.2.125 is like that. And then this one should be probably like that. Close enough. Okay. So solid line. Yeah, definitely not a fun one. So, oh no, don't curve away. Okay, solid line and we'll be above that one. Now, we need to be below that one. We need to be above the blue and below the green. Okay, this one's a little more of that conventional kind of look that you'd maybe expect to see or maybe want to see in these answers. It's going to be between these. Below the green but above the blue is just this kind of area right here. It's infinite, but its domain and range isn't infinite. The solution set is infinite. So there you go. Wherever these guys intersect, they think these actually intersected. No. Did they intersect at a whole number? I don't think so. Okay. There's that one. Okay. Number 25. That first one doesn't look factorable. So I'm not bothering with the intercepts. I am going to do standard form negative b over 2a stuff. I also wouldn't want to get vertex form by completing the square. So 2x squared plus x minus 5. The second one's really not better. They're making me upset with the next few here. This is going to be, how long have I been recording? An hour 15. They're going to make me pretty upset with these ones, guys. Given that we're not even halfway done number-wise. You wonder why I didn't record this video. No, I didn't know. I didn't have this PDF saved on my computer. Somehow I just skipped it. I don't know what happened. Okay, for the axis of symmetry, negative b over 2a. That's negative 1/4. So the y value I'll use decimal form. 1/4 squared is 1/16 times 2 is 1/8, so that's 0.125. And this is plus 0.25 minus 5. That's 0.375 minus 5, which is negative 0.4625, negative 4.625. I think that's negative 4 5/8. I'll kind of confirm. At least we'll know the y-intercept. So I'll confirm. Oh, the y-intercept. No, hold on a second. Then that's not right. How could the y-intercept be negative 5 and that not be lower? Let me check what I did wrong there. Okay, so among the glitches that I've had, I was paused and I didn't know that. I don't know when I paused. Did I pause talking about what happened to this number? Shoot, I thought I unpaused. I don't think the button pressed. So, guys, this is part of my rustiness, not checking it. So, I don't want to go back and redo it personally. So, let's say what's going on so far here. Because you probably missed my conversation that I had about how I graphed this one and how I'm graphing this next one. I just caught that I was paused. I apologize. Okay, so here's what's happened. If that was where I paused, here's what's happened. I mistook this. I had a plus here, and that's what caused that. It should be a minus because it is a negative 1/4. Okay? That will create this number here, and that's my y value for my vertex. Then I did the graph. Now, I didn't do the graph right on here. I actually did it at 0, negative 5, and then I shifted it over. A little cheat for me, but that's what I'm doing on this one right here, and I was going to mention that. But I caught that I wasn't recording. I don't know how many people are doing this problem anyway. So, okay. So here's what I started to do. I am graphing this one. This graph isn't any better when it comes to the vertex values. The x value is 2.5, the y value is 16.25. So here's what I'm doing. I'm graphing it at 2,16. You can't do this because you're not using software. I'm graphing it at 2,16, close enough. I'm doing this stuff to see what can fit, and then I'm going to draw the curve, and I'm going to drag it over just a little bit. I need a dotted line, curve. Line is fine if I say that, but I should say curve. A dotted curve, and ultimately we'll be shading below it. But of course, we're finding the overlapping shaded region with the other one that we'll be shading above, which has a solid curve. Okay, so let me shift this over just slightly at 2.5, 16.25, maybe something like that. So that's that little shift. What I was saying that you didn't hear because it was paused, and I apologize, is I was wondering why I don't do that more often on those weird decimal ones. I guess because you mostly have to follow along with me, and you had to here as well. But you know, these ones are more about the essence of not just the curve itself, which I know we're spending a long time on it, but also the essence of the overlapping shaded region, where we're shading and what we're doing. So why am I shading here? I'm shading below the green, below the dotted line, below the second inequality. But I'm shading above the blue one, above the solid curve right there, above the top inequality. And this is the overlapping shaded region of those two. Very, very long, arduous graphs. And you know what? As much as I feel bad that, oh, I skipped all the stuff, oh, sorry that you didn't hear me do it, and you know, I probably told a joke or two that I can't remember what I said and repeat. I mean, maybe my videos should do that more often anyway. I was just, you know, draw the graph. Okay, we'll come back and then we'll talk about the shading, right? Why do you need to spend time having me just do all those things over and over? I don't know. Took out some time in the video. Maybe it makes it look a little more, a little friendlier, that it's not as long. It's not 6 minutes longer now. Anyway, I like talking to you guys. Number 26. Y is greater than or equal to x squared minus 3x minus 6. Y is greater than or equal to x squared plus 7x plus 6. Now, I'm looking at the bottom one, liking that it's factorable, not liking that the axis of symmetry will be a decimal. The top one's not factorable at all. This one is not going to be much more fun than the last one, if at all. So if you didn't get to spend time with me on the last one and you are on this one, let's go. The axis of symmetry, not factorable, so we're going to do negative b over 2a, which is 3 over 2, or 1.5. I generally don't write the decimals here. I'm just doing it here just because. The y value, excuse me, we're going to get 2.25 minus 4.5, which is negative 2.25, minus 6, which is negative 8.25. So that's where our vertex will be for blue. Both of these will be solid curves shading above, by the way. Okay, I'll do the same trick as before. I'm going to be at 1 common negative 8. I apologize that you don't get to do that same. You don't have the same luxury. I think I'm already kind of checking out when it comes to the graphing aspects of this. So I really want to get these in. So 1, 1, 2, 4, 3, 9, 4, 16. And I can get close to, I can probably fit that 525. 25 up from that is 17. So I can kind of fit that. So I'm still gonna give you the points, right? Oh, one thing I did mention, it was probably when I was paused. One thing I did mention is the last question, number 25. I did need this tall of a graph. My vertex was up at 16 point whatever, 125 or whatever it was. I needed those 17 things. So you're welcome if I gave you this graph and you're using them. It was actually useful for that one. All right, so there's that. Now, this isn't in the right spot, right? This actually needs to be at 1.5, not 1. So like that, and negative 8.25, maybe negative 8.25 like that. So that's where they actually have to go. Now, the shading would be above. We'll wait on this next one and see what's going on. This one's actually interesting too, because these are both shaded above, and they're both upward facing, and they're both stretch factors of 1. So it's curious to see where this kind of goes and what it actually looks like overall. What would be really interesting is if one was within the other. Given that these are pluses here, will be on the left side, I think. So I don't think that's going to happen on this next one. Now, by the way, this one has a y-intercept of negative 6. Look what we're hitting. And probably the point that it reflects across. So my graph ain't too bad there. That's looking good. The next one does have y-intercept of positive 6. I'm going to put it there already. Well, I'm going to wait because I might do a shift. You know what? I'm not going to do a shift this time. You know what? I might do a shift. Okay. So, first of all, this one's factorable to x plus 6 times x plus 1. So that means it has x-intercepts of negative 1 and negative 6. So we can already tell over here it's on the left side like that. Now, the axis of symmetry is halfway in between at negative 3.5. Is that right? So kind of like that, negative 3.5. Now I got to plug in negative 3.5 to figure out the y value of the vertex. X is negative 6, x is negative 1. So y is, when I plug in negative 3.5, it's 2.5 times negative 2.5, which is negative 6.25. So negative 3.5 comma negative 6.25. You know what? Let's just do it from here. That way you could follow along with one again. Like old times. 1, 1, 2, 4. It's harder to count that. 3, 9. 4, 16. I don't know if I can fit 525 this time. It'll be slightly raised compared to the other one. But 4, 16. Oh boy, 10, just below 10, I think. I think right there and right there. Okay. Oh, and it should hit 6. Boom. And then 3.5 over 3.5 over should hit right there as well. So, I'm still getting some points with it. So, okay. Still solid, still shading above. So both of these will be above. So the overlapping shaded region will be above both of them simultaneously. That's what we got to kind of point out and find. Hey, not a bad curve. All right, so what's above one and above the other? It's going to be this area here. You can't call it a triangle because it's curvy, but where they meet triangularly. There you go. All right, that's above both of them. They're both solid like that there, too. Whew, okay, I don't know how many more graphs we're going to have like that. They might show up, but we'll see. All right, numbers 27 to 34, solve the inequality algebraically. Now, these are the one variable sets. If you weren't with me at the lecture portion, I'll try and say as much as I can to make sense of it as I'm doing the problems. We're going to do graphing after. They're probably not giving us good graphs. I'm looking at 42 and going, why did I choose this profession? But the graphs help explain what we have as well, even if I rough sketch one. So I might do that. I will do the sign chart still, but I don't always have to test points if we understand the nature of the problem. Okay, I'm setting this equal to, well, I'm setting this against 0 to start with. What I want to first find are critical values. Where do these cross the x-axis? When do I actually get 0 out? When do I actually get 0 out? So the first thing I'm going to do is I'm going to set this guy equal to 0. And then I'm going to solve this. Now, this is actually, I could solve using square roots. I could add 25 back over. This is actually factorable. 2x minus 5 times 2x plus 5. It's a difference of 2 squares. And then your two x-intercepts are 5 halves and negative 5 halves, plus or minus 5 halves. 2.5s, if you will. So these are the critical values. I'll call them CV. CV. Now, what I'm going to build here is what's called a sign chart that includes negative 5 halves, negative 2.5, and positive 5 halves, positive 2.5. If I plugged 5 halves or negative 5 halves into here, this specifically, this right here, I will get 0. 0 is not less than 0. So plugging these in will not get me true statements because this is strictly a less than. That means that at negative 5 halves and positive 5 halves, I do not get solutions. Is it in between these values that I get solutions or outside of them that I will? Here's where the graph of a quadratic would really help us as an idea. Not me graphing this, but giving the understanding of the graph. A quadratic equation has a vertex and it bounces back. You might know that this y equals this would have a stretch factor of 4 and a vertex at negative 25, and it goes upward. This is what the graph would look like, and this is the negative 5 halves and positive 5 halves right here. When x is between negative and positive 5 halves, your y's are negative, less than 0. That's what we're looking for. If I plugged 0 as x, remember there is no y. If I plug 0 into this x right here, I will get a negative value out in negative 25, and I will get a true statement. So this is where the y's are negative, or your result is negative, less than 0. This is where your results are positive, greater than 0. Those do not represent solutions to this thing. In my head, I'm explaining this right, but I understand if you're on the outside looking in, it's maybe not making as much sense. You don't need to draw the graph, but you want to understand the graph. And the easiest thing to understand about quadratics is if they have intercepts and you have a positive stretch factor, you're going to be negative in between and positive outside of. If it's upside down, you're going to be positive in between and negative outside of. And I think that's the best thing I can do with you here, the fastest one. You can plug in values though. So here's the idea that the book would ask you to do, that a teacher would bring up. Plug in a value to the left of negative 5 halves, plug a value between negative 5 halves and 5 halves, plug a value greater than 5 halves, like negative 3, positive 3, and 0. Plug them into here and see if you get true or false statements. The true statements represent your solution set. 0 would make a true statement, so will any number in between these two. Negative 3 would not be true. It would give you a positive number. Positive is not less than 0. Positive 3 would give you a positive number, also false. So your final solution set, your x's that do work for here are between -5/2 and +5/2. We write it as a compound inequality like that. There are other versions. We could use interval notation. We could say the word and. We do not include the 5/2. These are the solution sets. Here's the graph that represents it. You don't actually have to draw the graph with the number line. Oh, maybe you do, but that's the solution. Okay, number 28. Now, I'm probably not going to test points. I will state what points you can try testing and what will and won't work, but I'm going to go based off the graph nature. X squared plus 10x plus 9 is less than 0. Once again, factorable. This factors into x plus 9 times x plus 1. That means you're, whoopsie. Let's do the set equal to 0 version of this. I apologize. I'll do it on this side here. For critical values test, we set this equal to 0. We factor it, x plus 9, x plus 1, and you solve using zero product property, x equals -9, x equals -1. These are your critical values. These are your x-intercepts of a would-be graph. Now, the idea to me, personally, would be to do this. You want to plug in values. Oh, excuse me. The book's idea is this. Plug in a value to the left of -9, like -10. Plug a value between -9 and -1, like -5. Plug a value greater than -1, like 0. And see which ones will give you what kinds of signs. Because this is an upward-facing graph, and these are your intercepts, these would give you positives. This would give you negative. I need to get values that are less than 0. I need to get negative values. I need the set that's in between. Once again, -9, -1 will not count because we need to strictly be less than 0. If I plug in -9 or -1, I will be getting 0. I need to get the negatives. It'll look like the last answer in between these two, excluding these two values. But the values are now integers. X needs to be between -9 and -1. Number 29. I have x squared minus 11x is greater than or equal to -28. Now, you do want to set it against 0 before you begin your factoring process. Before you even set it equal to 0, I should say. We're setting it against 0 before we turn it into an equal sign. Now I'm going to turn it into an equal sign for the factoring biz. This does factor, or the solving biz. Not all of them are factorable, I imagine. I believe we saw some that maybe wouldn't have been. So your answers are 4 and 7 for your critical values. 4 and 7. So once again, my expression has a +1 stretch factor if I were to graph this thing not on a number line. If I were to graph this thing on axes, I would get positives outside of 4 and 7. I would get negative inside. That's the nature of an upward-facing parabola. I want ones that are greater than or equal to 0. 4 and 7 would give you 0. These are closed circle values. They count. They're included. They work. I want ones that are greater than. That means I want positives. Positive numbers are greater than 0. That's to this side of 4 and to this side of 7. Numbers that you might want to try test, I'll write them in. You can try 0. You can try 5. You can try 10. Right? Try and plug in those values. You plug in 0 into here. Oh, plug it into here, by the way. Plug 0 into here, you'll get a positive. Plug 5 into here, you'll get a negative. Plug 10 into here, you'll get a positive. That's what you're trying to look for. That's what you're testing against. I really got to highlight where you're testing it. You're not testing it here. You can figure out what's true and what's not true, but if you're trying to figure out what's positive and what's negative, this is the easier way to do the test. Anyway, your final solution set here, this one's a little bit different because it's a split. We don't actually write a compound inequality using a single statement with two symbols. We're going to do two separate inequalities. I can say x is less than or equal to 4, or, and the word has to be or, x is greater than or equal to 7. And it does include 4 and 7. So that's what the equal to portion is all about. See, I prefer to do these over graphing. Right now, I've graphed myself out, yet we're going to have to graph it a little bit. Good break from it for a little moment. Number 30. 3x squared minus 13x is greater than -10. This is the official adding 10 over. Oh. Adding 10 over right here. This is the inequality we want to do tests against. All right. Oh, that's a 0. I'm having trouble. Is it factorable? I don't know. Hold on. 3x x. Oh, yeah. Minus 1 minus 10. Negative 3 minus 10. Yeah. Oh, by the way, set it equal to 0 first. At this point, I'm writing equals 0, so we're all good. Now, my critical values, add 10 to both sides, divide both sides by 3, you get 10/3. Add 1 to both sides, you get 1. These are the critical values. 10/3 is 3 1/3. So when it comes, and remember, you're going to test against this one right here. For my sign chart, here's 1, here's 3 1/3, or 10/3. Values you can test, you can try 0, you can try 2, you can try 5, 4, whatever. Try numbers there. Once again, positive. As long as this, I'll tell you what, as long as our x squared is positive, this is going to be a plus minus plus. Plus minus plus. Now, which ones satisfy what we need? We need numbers that are greater than 0, positive numbers. 1 won't work, 10/3 won't work, and in between won't work. It's this side of 1 and this side of 10/3 that'll work. So our solutions, our x either needs to be less than 1 or our x's need to be greater than 10/3. Those will give us the positives. Those are the solutions to this whole thing. All right. Number 31. Whoops. Number 31, 2x squared minus 5x minus 3 is less than or equal to 0. It's already set against 0, so let's find the critical values by setting equal to 0. I think that's factorable. That's 2x minus 3 is minus 6 and plus 1. Negative 6 plus 1 is negative 5. Yes. All right, this is the factorization of it. Always try and factor where you can, y'all. Subtract 1, divide by 2, you get negative 1/2. Add 3 here, you get 3. So your two critical values are these guys. Let's make a sign chart, because you want to know where they belong in the sign chart as well. I would always do the sign chart even if I'm not actually plugging in points. I like to just make sure I got my placement right. It is a positive stretch factor, so positive to the left and right of your x-intercepts and negative in between them. So far, that's been the case. Now, to be less than or equal to 0, right? This is the thing we're testing against right here. To be less than or equal to 0. Equal to are these guys, the intercepts. Those work. Less than is negative. We want to be in between. So this is our solution set this time. Between negative 1/2 and 3. Between negative 1/2 and 3, like that. That should be our go on that guy. Okay. All right, number 32. 4x squared plus 8x minus 21 is greater than or equal to 0. Okay, no greatest common factor. I do not know if it's factor. I legit do not know if it's factorable yet. I'm kind of hoping it is. Given that it's another even, given that the last one was, generally the odds and evens kind of work with each other, so I'm going to guess it is. This is, if it's factorable, it'll be a 2x and 2x case, not a 4x and x case, because this number's even. 7 and 3, if it's going to work, the 7's positive, the 3's negative, like that. 14 minus 6, that's 8. So, yep, it factors. All right, that was the one test and it worked. So, x equals 3/2, add 3 divided by 2, subtract 7 divided by 2, x equals negative 7/2 there. So, boom. Your critical values exist here. Our sign chart will tell us what goes between things like that. Greater than or equal to is what we're testing against. Or equal to means these points will be fine. is once again a positive stretch factor. Only the last one is negative, actually. Positive, positive, and negative. What do we want? Not -1. What do we want? We want greater than or equal to. We want on the outside, we want the positives. So these guys over here, the x's that we want are less than or equal to -7/2 or greater than or equal to 3/2. Okay. Two more. Now for an equation, well, for an inequality, single variable inequality, absolutely nobody going to be stopping us when it comes to solving algebraically from multiplying everything by 2 if I want to. And I'm going to do it right now. I don't want the fraction. X squared minus 2x is greater than 8. Now I can subtract the 8 over. Greater than 0. This is my testing against set. That is very factorable. That factors to x minus 4 times x plus 2. Which means your critical values are 4 and -2. Okay, so 4 and -2. I didn't say points to test against last time. I apologize. I'll remember to do it this time. Okay, greater than 0. We want positives. I mean, for my sake, the positives are, with the positive stretch factor, going to be outside of here. Here's the negative, and these ones don't count. You can try plugging numbers like -3, 0, and 5. You plug in 0, you'll get a negative. Plug in -3 or 5, you'll get positives out of those, which is what we want. Numbers greater than 0, which will look like these guys here. Your solution set here is x is less than -2, or x is greater than 4. And you know what? I mentioned this in the lecture portion as well. Sorry if you didn't actually get it, but when I started talking about this set, I said it might have been better, for my sake, no, because I just did a bunch of graphs. It might have been better to do the solving by graphing ones first. The reason is because you understand the visual of what I'm talking about with the sign chart things. Am I actually testing the values? No. Should I be? Probably. But if I understand the graph, see, I'm not graphing, but if I understand what the graph looks like, I'm answering my own question by plugging those by not needing to plug those numbers in and saying what the signs are. And knowing that visual, I think, is very helpful for us. I do find merit and value in understanding what it means to plug in points to be solutions. And that's what the lecture portion's for. That's what's me telling you to try it. But there's a convenience matter as well, and understanding what I'm doing. This isn't a shortcut for me. It's shorter, but it's a matter of efficiency, right? Anyway, I am going to multiply this by 2. In a lot of solving cases, I would multiply by -2. But I'm going to keep this one negative so that we can discuss, and I'm multiplying by 2, by the way, so that we can discuss what it means to have the negative there instead. The upside down graph, if you will. Now, this also isn't factorable. So I'll tell you what. I'm going to pin this right here so we know what to test against. Conventional wisdom might say to use quadratic formula, and I think I will this time. It goes against my better, like, I prefer using completing the square, but because I'm maintaining keeping this x negative, you know what? I'm going to do completing the square. We will test against this, no doubt. No matter what I do to this equation for solving, there are only 2 solutions, and I'll get them no matter how I go about it, but we are going to test against this, which this is negative. Keep that in mind. When it comes to me solving, I'm going to multiply by -1, and I'm going to make it positive. When it comes to solving for the critical values. Now, it's still not factorable. That's not going to change. But I'm going to subtract the 2 over. I'm going to complete the square on these, and divide by 2 squared is 16. This factors to x minus 4 squared, and that's 14. Take the square root of both sides. This is faster than quadratic formula. And add 4 to both sides. So, 4 plus or minus root 14. Now, for the sake of these problems, you probably want to approximate them. 4 plus root 14 and 4 minus root 14. I'm getting around, I'm around to just one decimal place. Actually, let's do 2. 7.74. These are the critical values, by the way. 7.74 and I'm not gonna actually have an and there. 0.26. 7.74 and 0.26. So those are the critical values. 4 plus or minus root 14. Now, that means that 4 is in between these, right? I mean, 4 is literally smack dab in between these if you want a testing value there. All right, so 7.74 and 0.26. Now, let's go back to the original thing, right? This is what we're testing these things. Oh, geez. This is what we're testing these things against, this inequality up there. This is where, oh, my head just got kind of a fuzzy feeling. Plug in 0. Listen, I'll plug in 0 with you. You get negative 2 is less than or equal to 0. That's a true statement. Plug in 4 and plug in 8, right? You can try some of those. Now, because this is an upside down graph, you know, an upside down graph, woo, like that. These are negative over here. This is positive. So this is positive. These are negative. To satisfy this, we want to find ones that are less than or equal to. The or equal to's are the values themselves. Remember, these are approximate, though. The negatives are the ones that we want right here, like that. Now, you have to remember these are approximated. I don't know how to do like a approximately. How about this? X is less than or approximately equal to. I don't know if that's a thing. I think I'm making that up. 0.26 or X is greater than or approximately equal to 7.74. I like that thought. I don't know if that's right, but I'm going for it. All right. Cool. Numbers 35 to 42, we're solving by graphing. And I'm looking at them, and I don't think they're helping us very much when it comes to... Oh, you know, a few of these will be fine for integers. They just won't have x-intercepts that are good, which means we might still have to use quadratic formula or completing the square to get the intercepts. So it's not all graphing. We'll sketch the graph. And the graph's the visual. I might have been cheating using the algebra stuff. I probably should have been plugging in points, but I am going to actually sketch these graphs. So there's that. Or do we have to... Yeah, I'm going to sketch them. All right. X squared minus 3x plus 1 is less than 0. Now, you still want to pin it against 0. So you want to graph like a y equals version of this. Y equals x squared minus 3x plus 1. Now, this is not a favorable graph for us when it comes to vertex stuff. It's not factorable. So the x-intercepts we're going to have to find using other means, probably quadratic formula. I don't want to use completing the square with the odd number. And the vertex isn't good either. So nothing of this first problem is like fun, if that makes sense. So for the axis of symmetry, negative b over 2a is 3 halves or 1.5. The y value is 2.25 minus 4.5 is negative 2.25 plus 1 is negative 1.25. So your vertex is going to be at 1.5 comma negative, I'm getting a graph, 1.5 comma negative, or 1.5 comma negative 1.25. Stretch factor is 1. Now here's a point that we hit. We do hit the y-intercept of 1, and 1.5 over 1.5 over is like that. So we are going to hit that. But 2, 4, 3, 9. Now all this stuff to graph, listen, I'm going to stop after 3, 9. I think there. Is that too high? Right there. Okay, I'll stop after 3, 9. The idea of the graph now is that we crossed x-intercepts, and I don't know what they are. Neither do you. They're not integers. They're not even rational. This wasn't factorable. So we got to find out what they are. And we have methods, one of two, quadratic formula or completing the square. And I'm actually going to use quadratic formula. So, again, when set equal to 0, that guy, right, for the critical values, my discriminant is b squared minus 4ac, which is 9 minus 4, which is 5. So, x equals negative b plus or minus the square root of b squared minus 4ac all over 2 times 1, 2a. So these are the values for this quadratic formula. It didn't take too long, but I do have to compute those. So I got to do 3 plus root 5. I'm doing this in my calculator right now. 3 plus root 5 divided by 2. And I'm getting, still a lot to do there, 2.62 about, and then 3 minus root 5 divided by 2. I'm getting 0.38, like that. Now, what we need to do with those intercepts is recognize these are the critical points. I don't know if we have to sign chart it, per se, because we kind of have a sign chart here. We need to find the ones that are less than 0. Right? So this is the idea that we were talking about from the other set. Here are those intercepts. This is my 0.38. Here's my 2.62. And you know what? Those track. Those look like the things, right? But which ones are less than 0? Below the x-axis. Between them. Between them are the ones that are below like that. So my solution set are these ones here. The x's that are between 0.38 and 2.62. And that's what I want to write as my answers. So 0.38 is less than the x and less than 2.62. You know what I can't do here is do any squigglies with those equal to's. So I'll say about or approximate, about between those two there, not including them, just between those two. And I hope not every problem is like that when it comes to the solving mechanics. I don't think they will. Like this one, I think is better for a lot of reasons. Even if it's not factorable, I can still solve by completing the square. And I don't think my vertex is fraction, decimal. So this one should be better for me regardless. And you. So on number 36, what I'm going to first do is, I'm going to graph it first. Let's do a y equals graph version of this. Our I kind of want to do completing the square. Our axis of symmetry, the x value is negative b over 2a, which is 2. The y value is 2 squared minus 4 times 2 plus 2. That's 4 minus 8, which is negative 4 plus 2 is negative 2. So your vertex is at 2, negative 2. And the stretch factor is 1. This one I probably don't mind just going up. 2, 4. And notice y-intercept of 2. That works. 3, 9. And 4, 16. 16 up from negative 2 is 14. Okay. So here... Ooh, bad plotting. All right, here's our curve. Now our curve does not hit rational integer x-intercepts, much less rational x-intercepts. So we're going to find those ones by setting this equation equal to 0 and solving. I will be solving by completing the square because I do have a 1x squared and an even linear coefficient. So by completing the square, this number will be 4. Divided by 2 and square it. This factors down to x minus 2 squared, and there's a 2. Take the square root of both sides and add 2 over. So 2 plus or minus root 2 are those values. Notice that 2 is the axis of symmetry x value, so we're adding root 2 and subtracting root 2. I know root 2 is around 1.4, but I don't know the numbers after that, and I want to round to 2 decimal places. So 2 plus the square root of 2 is 3.41 about. and then 2 minus the square root of 2 is around 0.59. I probably should have known that. Okay, now we need to test against this, greater than 0. The numbers, the x-intercepts themselves are when y equals 0, when we get 0. Plugging in 3.41 and 0.59, about. Here are the greater thans. The greater thans are right here and right here. It's the x values that are left of it and right of it. The upward facing graph. We're pretty much doing them algebraically again. We're sketching a graph, but everything that I would have done before, I'm doing now. So my final solution set here is less than this one, the smaller one, and greater than the bigger one. So x is about less than about 0.59, or x is greater than the 3.41. These are once again about that, because these are irrational, and we rounded those. I kind of want to find a way to say that approximately. I don't know if that's accurate, but that's how I'll do it. Number 37. Once again, this one shouldn't be bad. In fact, this one is factorable. X squared plus, so I don't know why they started off on 35 in that like rut. We'll pin it against 0 in greater than fashion. We will be graphing the y equals of this. I kind of want to do this by factored form because it's factorable. X plus 7 times x plus 1. So that gives us x-intercepts of -7 and -1. The axis of symmetry is halfway in between at -4. -4 plus 7 is 3. Hold on, we do some different color. Axis of symmetry is x equals -4. The y value for that, 3 times -3, which is -9. So this graph, -4, -9, has a stretch factor of 1, 1, 1, 2, 4. There's our 3, 9 right there. 416, it's at y equals 7, right? 416, boom. So everything's kind of tracking the way we want it to. And 525, oh, something just happened. And 525 right there. All right. Big ol' parabola. I hope I'm unpaused. I'll flip my lid if I'm not. Hold on. We're still rolling. Almost 2 hours. Okay. Now, you might be wondering why we're not doing shading here. This isn't two variables. We're trying to figure out what values of x make these things true. The shading is finding what xy ordered pairs satisfies the thing pinned against it. This isn't a boundary curve. This is finding out what x values give us positive y values or negative y values or whatever like that. Because this is the thing we're testing against right here. This is what we're testing against, right? This is what we graphed. Y equals this. And we're trying to see the numbers here that are greater than 0. So the x-intercepts wouldn't get you 0 right here. No. But the ones to the left of this and to the right of this would give you 0. Greater than 0. Give you positives. So less than -7, right? Those are my critical values. And right of -1. So we want to say, for that to be our solutions, we'd want x is less than -7 or x is greater than -1. Those are the positives. I feel like I was doing that with the number line problems before, solving algebraically. We didn't sketch the graph, but we had the idea of the graph. It's upward facing. Those would be positives. These would be negative. So it's the same effect. And as long as the graphs are integer values, I'm not going to hate too much. So this one should also be good. Not factorable, but integers. X squared plus 6x is less than -3. Add the 3 over to begin with. And we'll sketch the y equals version of that, like that. The axis of symmetry is at -b over 2a, which is -6 over 2 or -3. The y value will be 9 minus 18 is -9 plus 3 is -6. So our vertex is at -3, -6. We do have a stretch factor once again of 1. No good x-intercepts here. So this is where we're going to have to use completing the square quadratic formula, and I'm going to use completing the square. So -3, -6. We've got ourselves a 1, 1, 2, 4, 3, 9 scenario. Now the 3, 9, we should be hitting y-intercept of 3, and we do. So that pans out. And 4, 16. There. All right. I think that's all I can fit. Oh, pretty nice. Not bad. I've only drawn like 20 of these. Probably a lot more, but some of them dotted, so I'll cut myself some slack. Okay. Yeah, what are those x-intercepts all about, right? Now, first of all, the x-intercepts won't end up counting. Like, they are... Yeah. We need to find ones that are less than 0. It's going to be the in-between these two x-intercepts. We got to find out what they are. I'm going to use completing the square. Set this equal to 0 and solve. Subtract that 3 over. Let's divide by 2, square it, divide by, or whatever, add 9 to both sides. This factors down to x plus 3 quantity squared, and that number 6. Take the square root of both sides. We get plus or minus square root of 6. Subtract that 3 over. You get -3 plus or minus the square root of the 6. Now, approximating those, I can't help you. The calculator will have to. -3 plus square root of 6 is negative. Oh, it's still negative. Oh, yeah, duh. Negative 0.55. And that looks like a negative 0.55 to me. Sure. And then this other one, -3 minus root 6, is negative 5.45. About. So those are the critical values that we're talking about. Which ones will keep us, again, this is the thing we're talking about, less than 0, are the ones underneath. They're just in between negative 5.45, which is the left value. This is the one on the left. Negative 0.55 is the one on the right. So we're going to say about, because it's irrational again, being between negative 5.45, non-inclusive, and negative 0.55, like so. All right. Okay, number 39 is an example of one, if not factorable, that I'm not a fan of. I'm not a fan of the graphing, but if it's not factorable as well, that means we have more to do. Okay, we're going to add 2x to both sides. We do have to graph this. I see no reason why this is factorable. Let me test in my head. Let me test to see if this is even factorable, just so I know what we're dealing with here to begin with. Oh, it might be. -6 plus, 6 minus 4. 6 minus 4 is 2. So it is factorable. So there's a y equals. Not only factored form, or intercept form, but it's the graph's still gonna suck. So I'm gonna use I'm actually gonna use negative b over 2a for this one. It's still gonna suck. Negative b over 2a. That's negative 1/3. I am gonna make this one of those graphs where I am plotting at like a normal value and then I'm gonna shift it. Sorry. The y value. 3 times negative 1/3 squared. I'm getting like carpal tunnel. 3 times negative 1/3 squared plus 2 times negative 1/3 minus 8. Negative 1/3 squared is 1/9 times 3 is 1/3 minus 2/3, which is negative 1/3 plus 8 is, I don't know, I'll say 7 2/3 this time. Normally I go for the improper fraction thing, but just 8 minus the third. So when it comes to the graph, because see, it's factorable. I already know where these things factor. I could probably tell you all the answers from there. But if we want to plot the actual points, we're going to be doing... Wait, this goes upward? Oh, this must be negative 7 2/3. Okay, that makes more sense. All right, negative 1/3 comma negative 7 through. So here's what I'm going to do. I'm going to plot it at like, first I'm going to start at 0, negative 8, and then I'm going to do some shifts after that. Sorry, that's what I'm going to do. My stretch factor is 3, 1, 3, 2, 12. 12 up from 8 is 4. 3, 18. No, 327. That probably won't fit. That won't fit. Forget about it. But it will still be curvilicious to an extent. Now I still do have to shift this guy. Okay, so that's locked. Good. Okay. Negative 1/3. I don't know. And negative 7 2/3. Probably like that. Okay. Now, what should be an agreement here? This should hit a y-intercept of negative 8. That's... Did I do something wrong? Oh, not negative 7 2/3. I'm sorry. Hold on. I guess it's a good thing that I did what I was doing here. So hold on. I'll shift that. I'm sorry. It's not 8 minus... This is a minus 8. That's why I did put 7 2/3 the first time. This is negative 8 1/3. Okay. So I just got to shift it the other way. So I'll do it like that. So my y-intercept should be... This is why I check these. My y-intercept should be negative 8. That's good. My intercepts, my x-intercept should be negative 2. Now, that's negative 2 right there. So my curve, obviously my curve is fat and bad. So let's fix that. Because I really do want to hit that x-intercept. That's one of the natures of the thing, right? So I should be hitting more so, I guess like that. Boom. And then I should be hitting, this is 4/3. Add 4 divided by 3. That's 4/3. So that probably should be even fatter, but you know, like over there. So it's whatever, right? They're within that idea. And that's what we want. Now, we got to be less than, here's the thing to test against, right? This guy right here should be less than or equal to 0. The ones that are equal to 0 are the x-intercepts themselves of negative 2 and 4/3. The less thans are the in-betweens. So for that set, boom, x needs to be everything between, and these are exact numbers. X needs to be between negative 2, and I'm not doing any decimals here, 4/3. You want to say that actual thing there. That is 4/3 from this. That's where factoring kind of helped. I didn't want to use quadratic, or, you know, I would have solved by factoring it. But that's where that helps to give me what I'm looking for there. Oh, what's that? Number 40. Get a water hit. Okay. 3x squared plus 5x minus 4 is less than 0. Oh, that doesn't look factorable. I'm not sure. Hold on. I was hoping it would be a minus 2. I think minus 2 would have been factorable. Minus 4? I think minus 2 would have been factorable. I was hoping for that. Okay. Not factorable. Not pretty. My least favorite problem of the day, right? So, you know, part of me making these videos, it helps me recognize which problems I should assign to students and which ones I shouldn't. I ain't assigning this to my students. I don't want to give them the headache. You know, they're not going to be tested on a question like this. They're not. They won't do this problem. That's probably me not giving them enough perseverance to want to do it. But no, they'd stop. Negative 5/6. I mean, what? Right? Anyway, I'm not even going to write the decimal for that. Negative 0.83 repeating. No. Okay, let's keep going. The y value for that, it's really hot in here. 3 times, and I know I'm wearing the jacket, but it's just in general, even if I take it off, it's really hot in here. Negative 5/6 squared. I might cool off after this section of problems. plus 5 times negative 5/6 minus 4. Boy, I wish this was at least factorable, because yikes. Okay, 3 times 25 over 36 minus 25 over 6 minus 4. Now 4 I'm going to put as 24 over 6. So I can work on those ones. This is, well, this will be over 12. Hold on a second. So, let me do that part later. 25 over 12 minus 25 over 6, which is negative 25 over 12. So over 12, 48. 48 over 12. So negative 25 over 12 minus 48 over 12 is negative 73 over 12, which is whatever number that is. Negative 6 and a 12th. I mean, for my drawing's sake, that might as well be negative 6. I'll go ahead and say that. So the negative 5/6 almost might as well be negative 1. So I'm going to graph it at, I'm going to do the shift thing. I haven't done that very much, but I'm doing that here. They're giving us ridiculous problems. I'm going to fight back. Negative 1 comma negative 6 and a 12th. And I only hope that that graph is actually right, that I didn't mess up a fraction portion. And then the stretch factor is 3. 12 of 12 is 6. And that's really all I'm going to fit. So let me graph this first. And then... Whoa. Then we'll do a little shift of it afterward. Little curvy, which can be a problem for the x-intercepts when we talk about what it should be hitting. But since they're irrational, I don't know if we'll notice it anyway. So let's just say that. Okay, so that, or at least we're good with little room for error. Negative 5/6, just a little bit over like that. Negative 6 and a 12th just down. So I'll pretend like it's like that. With the y-intercept being negative 4, that looks good there. There's my y-intercept of negative 4. So that does look good. Remember, this is what we're going to be testing things against, but we still don't know those x-intercepts. I imagine one x-intercept is going to be somewhere around 0.5, and one's going to be somewhere around negative 2.1. I don't know. Negative 2.2. So, yeah, I don't think it's factorable. So let's go ahead and use quadratic formula. I'm going to set 3x squared plus 5x minus 4 equal to 0. Our discriminant, b squared minus 4ac, gives us 25 plus 48. Oh, it's that 73 number. Hello. Which is 73. Non-perfect square means irrational, means they made the right choice of not trying to factor. X equals, now the rest I just got to do here, negative b plus or minus the square root of b squared minus 4ac over 2 times 3, so over 6. So your two approximations, again, I'm guessing around 0.5 and around, just from the graph, around 0.5 and around negative 2.2 or something like that. Negative 5 plus square root of 73, and then divided by 6. So this is the, okay, this is the positive one. It's 0.59. So I was close. And then the other one, negative 5 minus root 73, and then divided by 6. At least I think my graph is right then. Negative 2.26. Well, that's pretty close. All right, now those aren't the answers. These are just the intercepts. So what do we want? We want less than 0. We want the ones that are between here, right? That makes them negative, but not including these ones here. So between the smaller one and the bigger, the negative one and the positive one. So the way we want to write the final answer is between negative 2.26 and 0.59, whereabouts, thereabouts. Those are the ones that are less thans. All right. Okay, number 41. I don't know if it's factorable yet or not. I'm going to have to multiply by 3 and see what's... I don't think it is, because those are both the same number. So number 40, at least I don't think it's going to be bad. Well, I'll tell you what. Would they want me to, I guess they want me to graph this. So put it against 0. I think they still want you to graph this. You know what I mean? Like as is, even if I solve using different means. So I will. Yeah. Okay. So 1/3 x squared plus 2x minus 2. Okay. So not factorable. I'm just going to tell you right now. Even with a GCF of 1/3. So your axis of symmetry, we got negative b over 2a. Now, I don't think this ends up being bad for an x value here. It's negative 2 over 2/3. Dividing by 2/3 is multiplying by 3/2. So negative 2 times 3/2 is negative 3. Excuse me. That'll probably go in the way of my graph. So let me shift that. And yeah, the y value should be good as well. So 1/3 times negative 3 squared plus 2 times negative 3 minus 2. The stretch factor is a fraction, all right, but the vertex isn't. And that kind of matters more to me. 9 divided by 3 is 3, minus 6 is negative 3, minus 2 is negative 5. So negative 3, negative 5 is the vertex. Okay, not a bad one. Not a bad vertex. Now, I don't think it's factorable, so I think the intercepts are, whatever. But we'll start with that. So negative 3, negative 5. 1/3 stretch factor. Over 1 up 1/3. Over 2 up 4/3. So 1 1/3. Over 3 up 9/3, which is 3. And there's my negative 2 y-intercept. Over 4 up 16/3, which is 5 1/3. Yeah, kind of irrational looking right there. Over 5 up 25/3, which is 8 1/3. 6, 7, 8. Over 6 up 36/3, which is 12. I will stop there. 12 up is 7. I will stop there. I'm kind of running out of room on that left side anyway. Too many thirds to deal with. Yeah, turds. Point is, I crossed the x-axis and I do believe my graph based on the y-intercept. Not only do I believe it, it's right. So what are my intercepts? Well, first of all, here's what I'm testing against. We need to find out the positive ones. They'll be outside the intercepts. No, this isn't hitting exactly at negative 7. It is a less than. It's like negative 6 point something, and this is a little less than 1, a little left of 1. So we're going to be on the outsides of these values right here. We just got to figure out what they are. Okay. Now the equation here, the inequality here, or thing here, I can make as an equation set equal to 0, right? So 1/3 x squared plus 2x minus 2 equals 0. Now in terms of solving, I'm going to multiply everything by 3. This is just me solving. You can probably tell not factorable. No two numbers multiply to negative 6 and add to positive 6. I will use completing the square, given that that's an even linear coefficient with a 1x squared here. That number's 9. None of these imperfect squares have been simplifiable. We haven't been able to practice that at all. So x plus 3 squared equals 15. We have had a pretty good balance, though, of doing some of them factoring, some of them completing the square, some of them quadratic formula. So we do get some good practice of all of those things here. Negative 3 plus root 16 is 4. So this is a little more, I'm going to guess, this is a little, well, I already said it. It's a little less than 1, and it's a little more than negative 7, right? It's like, like that. So everything's looking right. So negative 3 plus root 15 is 0.87, approximately. And negative 3 minus root 15 is negative 6.87. Like that. So those two are those like values, and we got to stay outside of them to stay positive. So we'll do an OR case for our final answer. We'll say x has to be either less than or equal to negative 6.87, or, I hate writing it kind of in this slot, x is greater than or equal to 0.87 about skis. that's the final set on those ones. Number 42, we don't do a lot of 3/4 stretch factors, but we'll deal with it. I do wonder if there's factorability. Number 42, 3/4 x squared. My only hope is the vertexes integer values. From there, I can deal. You know what I'm saying? Subtract 3 over. That's what we're going to pin things against, because we're going to be graphing y equals that guy. Now, in order to do that, see, I'm curious if it's factorable first, because then I can get the intercepts. I'll do the vertex first. Okay, so we'll do negative b over 2a. That's negative, that's 3 halves. Negative 4 over 3 halves, which is negative 4 times 2/3. Oh, no. That's negative 8/3. All right. Negative 2 2/3. Oh, no. Another problem not to assign for my students. I hope teachers watch these and say, well, you know what? They probably, I don't know if the answer key has the graphs on them, but if it does, they probably can look at that and say, yeah, no. 3/4 times negative 8/3 squared plus 4 times negative 8/3. For me coming back to all this was not the section to come back to with these graphs. I will cool off after this. Probably keep the jacket on. Okay. So 3/9 reduces to 1/3. 64/4 reduces to 16. So 16/3 minus 32/3 is negative 16/3. Minus 3, which is 9/3, and that's negative 25/3. So negative 8/3 comma negative 25/3. That's also, hold on, I'm going to kind of write that out, because that's negative 2 2/3. Normally I don't say things that way anymore. Whoops. Negative 2 2/3 comma negative 8 1/3. That's my vertex ultimately. As you've seen, I'm not going to start like that. I'm going to start on some integer values, and then I'm just going to move it on over there. So I'll start at negative 2, negative 8. And my stretch factor is kind of weird too, right? It's 3/4. Over 1 up 3/4 of 1. Over 2 up 3/4 of 4. That's 3. 3/4 of 9. Oh, I'm going to have trouble with some of these actually. Is 6.75. I'll probably say it in fraction form first before. But 3/4 of 16 is 12. So that one's kind of easy enough. I might even stop at 12. We're already there. 12 up from negative 8 is 4. I'll probably just stop right there. Sorry. We have some of the graph. I always say plot as many points as you can fit, but not one in there as unreasonable as they've been. I still got to shift this too. Just barely, but I got to shift it. All right, so we're shifting this to, let's lock that, negative 2 2/3, kind of like that, and then negative 8 1/3. Maybe like that. Okay, we were expecting a y-intercept of negative 3, right? I think, yep, negative 3, and yeah, we got it. So here's my y-intercept of negative 3. Now the x-intercepts, I would believe that this is more than negative 6, like negative 6 point something, and this is less than 1, or whatever. That's the whereabouts of this. Maybe on this side of it. But I don't yet know if it's factorable. So let's try that. 3/4 I don't know. 3/4 x squared. No matter what, I got to set it equal to 0 and do all that. Plus 4x minus 3 equals 0. I am going to multiply everything by 4. 3x squared plus 16x, what did I say? 4 minus 12 equals 0. Oh, I'm so curious. Give me a second. I got some things to test with this. 6 and 2. 6, 2. Does that work? Plus 6 minus 2? 18 minus 2 is 16. It is factorable. That means this was negative 6. It wasn't left or right of it. It was on it. And this is 2/3. Okay. So it was factorable. So this number is my 2/3. Wait, is this equal to? Greater than or equal to? This is my 2/3. This, boom, it's hitting right there. That's my negative 6. Okay, we need to be greater than or equal to it, which means the above skis over here. So to this side and to this side, we have to be less than or equal to negative 6. X is less than or equal to negative 6, or x is greater than or equal to 2/3. All about being exact. Now, no one's stopping us, guys, from using quadratic formula, but you better simplify to these numbers when you do. Right, make sure you get fully there. It's just if it's factorable for me, it's faster. Now, how did I know it was 6 and 2, you might be asking? I don't know if you know my factoring biz, but because this is an even number with only odd factors, these would have had to have both been odd, which is not possible with a factor of 12 or both be even. 6 cannot go with 3 because there ain't no GCF and there wouldn't be here, so I had to place the 6 there. It was my only possibility. There are no other two even factors of 12. 12 and 1, 4 and 3. So that was my only shot. Okay, it wasn't dumb luck. It wasn't me knowing beforehand, anything like that. Anyway, let me pause. I'll be right back. All right. Hope I'm good. All right. 42 done. Okay. 43 and 44 on this page. Number 43. Drawing conclusions. Consider the graph of the function f of x equals ax squared plus bx plus c. All right, we don't see any y-axis here, so deal. What are the solutions of ax squared plus bx plus c is less than 0? So we need to be less than, which is underneath the x-axis here. We cannot include the x-intercepts here. So in between x1 and x2 for part A. All right, your x's, so x sub 1 is less than x, which is less than x sub 2. Those are the ones, that's the betweenness. I won't do the box. That's the betweenness of that. Part B, what are the solutions that are greater than 0? Those ones would be, again, non-inclusive for x1 and x2, but the ones above the x-axis here for positive y values there, which are to the left of x1 and to the right of x2. I probably shouldn't be doing it up on the curve. I should be doing it more like this. Boom. I think the notes kind of did that. And boom. So x is less than x sub 1 or x is greater than x sub 2. Part C, the graph of G represents a reflection in the x-axis of the graph of F, for which values of x is g of x positive. If it's a reflection in the x-axis, it's going to be this way. Okay, this would be your g of x graph. The x-intercepts would be the same despite my, you know what, I can shift this a little bit. There we go. It would kind of maybe look more like that. So this would be my g of x for here. So now it's positive in between, just like A. I can copy and paste this, and part C, this is where g of x is greater than 0. G of x is greater than 0. That's when they're positive, once again, in between, as it's a reflection. All right, interesting question. All right. Okay, number 44. Modeling with mathematics. A rectangular fountain display has a perimeter of 400 feet and an area of at least 9,100 feet. I think that would be square feet. I don't mean to correct the book. Wait, hold on. There was a lecture problem that had this. Did they say square feet at the time? I'm very curious, and I'd like to check right now. Hold on. Was it this one? Yeah, they said square feet at the time. They messed up here. They messed up here. Typo. Should say square feet. I'll put feet squared. Looks like a question mark, kind of. Feet squared? Feet? All right. Now, it is like that lecture problem. If you were with me on the lecture problem, you might know what to do. Or you might not. It might have been a little confusing. So, first of all, rectangular fountain display. All right, rectangular. Widths are equal. Opposite widths are equal. Opposite lengths are equal. A perimeter is 2 lengths plus 2 widths. And an area is length times width. Now, for the sake of this problem, our perimeter needs to be 400 feet exactly. 2 lengths plus 2 widths must be 400. The area must be at least, so greater than or equal to, 9,100 square feet. Now, what we're going to do, and this is what the example did at the time and such, and I think they used the graphing calculator, so I'm going to do that too. We could solve algebraically. We will solve for one of these variables, L or W. It's going to make 0 difference because they're both multiplying by the same coefficient. I'll solve for L. We're going to solve for L. 2L is 400 minus 2W. Whoopsie. Actually, you know what? It does. Wait, describe the possible widths. Yes, I do want to do this. It does matter. You want to solve for L so you can substitute in the expression that contains W. Divide by 2, you get 200 minus W. Now, this expression is going to take place of L in the inequality for area here. You are now going to have an inequality that states W times 200 minus W is greater than or equal to 9,100. This is a quadratic inequality. If I distribute W here, you get 200W minus W squared is greater than or equal to 9,100. You know what? I might just solve this conventionally. Now, if the book were to do this, they would subtract 9,100 over, put it in standard form and graph it. I'm going to add W squared over, therefore subtract 200W over. Keep 9,100 positive. The problem here is you got to figure out which side of 0 it's on. If I add this over and add this over, this is where 0 is like that. Notice how it goes that way? That means it's going to go this way as well. That's what it should look like. So we need to solve for W in this scenario. Now here's what I'm going to do. I don't know if it's factorable. I'm going to assume it's not. I'm going to actually use completing the square on this. I know they probably use the graphing calculator. Let's practice, guys. At least W squared is positive. That was the most important part for me for that. Oh, 9,100, not 900. 9,100 is subtracted over. Here we're going to add. Divide negative 200 by 2 is 100. Squared is 10,000. We're going to add 10,000 to these. Oh, this might be factorable. That's a 900. I take it back. I'm going to try and factor it. I'm going to try and factor it. I didn't assume it was going to be factorable. Two numbers that multiply. Oh, I don't know factors of 9,100. 91 and 10. 910 and 10, excuse me. Maybe I shouldn't have factored it, even if it's factorable. You know what? I won't factor it. I don't know what it factors to. Oh no, I lost my completing the square stuff. Uh-oh. Let me think of the factorization. Sorry, guys. Hold on. Okay. I think I had them. I was trying to divide by 3 and I couldn't, but 13 I think it can. It's 13 and 7. So 130 and 70, I think, are the numbers I was going to do. So if 13 and 7 give you 91, then 130 and 70 give you 9100. Now that probably was more worth doing completing the square at that point. I just figured if it's factorable, I kind of want to factor. So my widths here, remember these are critical values, by the way, 130 and 70. These aren't the answers, these are critical values. CVs. If we're doing this algebraic solving and not graphing, the number line instance is the best approach to this. Given that this is a positive w squared, we have to be between 70 and 130 for our widths. These would give me, whoopsie, negative, not negative widths. These would give me negative values that satisfy this inequality. These are positive widths between 70 and 130, right? But they give me negative values when substituting in there, which is what we're trying to do. Find numbers that are less than or equal to 0 in that setup. Because I flipped everything over, right? I'm the one who added w squared over. So I need my widths to be between 70 feet and 130 feet. That's how I'm going to write it out. Now, if I have another question like that coming up, and I don't know if I do, I'm probably going to use the graphing calculator. That wasn't necessarily hard or bad, but after pausing on the factoring, the widths, the possible widths of the fountain, the fountain of the fountain must be between 70 feet and 130 feet. Now, I'm not double checking anything with that. I'm just going to go ahead and say that's right. But what I mean is that you can do some double checks by like plugging in a width that's like, like 100, right? You can plug in 100 for the width and check the length. I guess the length would also be 100, and 100 times 100 as long as it's more than 91. You're good. Actually, that would totally work out. But anyway, so that's just kind of what I'm looking at there. Okay, number 45. I'm probably going to use a graphing calculator for that formula, for that equation we're seeing there. The arch of the Sydney Harbour Bridge in Sydney, Australia, can be modeled by that, where x is the distance in meters of the left pylons. X is the distance in meters from the left pylons, and y is the height in meters of the arch above the water. For what distances x is the arch above the road? All right, so 45, y equals negative 0.0021x squared plus 1.06x. Okay, now, yes, I will be doing something with the graphing calculator eventually, I can guarantee you. What we're trying to find is, the road is here. Let's use a good color. Can you see green? That's not green. Red. All right, the road is here. 52 meters above the water. The arch, intersects those points of the road. We need to find out when these parts are, it says above the road. If the road is 52 meters above, then I'm assuming anything above 52 meters is parts of the arch that are above the road. So y is our 52. We need our thing. Let me write it over here. We need our thing here. I don't know what I just wrote. Plus 1.06x to be greater than 52 meters. At y equals 0 is the water. At y equals 52 is the road. We need our arch to be above the road. So this is what we're looking at. So what I'm going to do is graph y equals this instead with the minus 52 in mind. Listen, there are a lot of ways I'm probably doing this the hard way, but 52 needs to be involved. So you know what? I'm kind of doing this the hard way in that, okay, here. I'm not going to do this bottom part. This part here is fine. What I'm going to do is graph. I'm going to sketch two graphs here so you can see what it originally looks like. I'm going to sketch this one, and I'm going to sketch y equals 52. And then we're going to find their points of intersection. It's not the intercepts, but it's their points of intersection, and that's the betweenness where you're going to see the aboveness of it. We need to be between those two values to be above the road in those two values. So I'm going to use my graphing calculator here. we're going to do y equals negative 0.0021 x squared plus 1.06 x. Excuse me. Oh, y equals 52. All right. So my window range, what does this go to? It doesn't say how far it goes, but from 0 to, I don't know, let's see what 400 does. And then, whoops, 0 to 400. I don't know how long the road is, but it's at least 52 meters high. Let's go to 150. All right, let's see what we have here. I gotta stretch it out a little more. It's more than 400 meters. All right, let's see. Okay, so there's like the arch in the road, right? So what we want to do is find their points of intersection. I'll hit trace. Oh, not trace. I'll hit... Oh, I'm hitting all the wrong buttons. I'll hit calc, intersect, first curve, second curve, and let's find the rightermost value, this one here. 449.698. I'm going to round that to about... I'm just going to write it on the screen here. 449.7. And the other one... Let's put 0 as my guess. 55.06. Okay, so what we're doing is we're saying that these two values are what we need to stay in between for that drawing. This is 55.06 meters away from the left pylon. This is 449.7 meters away from the left pylon. We need to stay in between them to stay above the road. So what I'm going to write as my final answer there is about... Whoops. Between... I did that again. About that and that. Okay? From the left pylon. Okay. Number 46. The number T of teams that have participated in a robot building competition for high school students over a recent period of time in years can be modeled by this. I wonder if there's any accuracy to that model. That's sure. So number 46, T of x equals 17.155x squared. Now between 0 and 6, so if we're going to use the graphing calculator, which I kind of hope we do, I'll make sure to stay in between there. After how many years is the number of teams greater than 1,000? Justify your answer. So this is just another one, guys, where I'm just going to... I'll graph y equals this. This will be like my f of x. F of x equals this. And then I'll make a g of x equal to 1,000. And I'll find out where they intersect in this set. See, it'll cross 1,000 probably twice. But you will only probably see it once within this domain. Within this domain is probably just going to do it once and take off from there. So what I'm going to do is go back to the graphing calculator. I'm going to... make those two equations, the bottom one being 1,000, and then this being this 17.1. Oh, what did I just do? 1,000, and then 17.155x squared. Huh. All right, the good news about this is I know for my window range, I'm going to go from 0 to 6. And I know that it's going to at least hit 1,000. So, it's, I don't know, 1,500. Why not? So, it'll probably just, we'll see 1,000 cross. And yeah, we don't see the other time it hits 1,000 because it's in negative land. And we don't really care about that. So, let's find out where they intersect here. All right, 3.0 0.096. I'm going to round that up to 3.1. Wait, what is this? This is in number of teams have participated over a recent period of time of X in years. So this X is 3.096. I'm going to say about 3.1. So X is about 3.1 there. Now notice for the curve, we need to figure out when the teams are greater than 1,000. So based off the curve, it's going to be past the 3.1 number, right? The curve that we see on that window range is, there, and we need to be greater than it. We need to be on this side of 3.1. So X has to be greater than 3.1 years. I don't know if that's the best way we're supposed to say it. I don't know if we're supposed to say from the 4th year onward or something like that, but I'm just going to say there, greater than 3.1 years will have more than 1,000 teams. All right, whoops, I got to bring the thing down. Number 47. Problem solving. A study found that a driver's reaction time A of X to audio stimuli and his or her reaction time V of X, this is cool, to visual stimuli both in milliseconds can be modeled by this. So we have a greater, I don't know. I'd say we have a greater visual than audio because light travels faster than sound. I don't know. Anyway, we'll see. A of X equals. This is cool. This is cool because this is probably scientifically accurate. I'll let them just keep the domain. I'll use it when I go to the graphing calculator. Oh, excuse me. X is the age in years of the driver. Oh, okay. Write an inequality that you can use to find the X values for which A of X is less than V of X. Well, so part A. So, okay, we're just going to do this. 0.0051x squared minus 0.319x plus 15 is less than, 15, is less than 0.005x squared minus 0. I don't think we have to simplify this or set it equal to, I'm having trouble. I'm telling you, I am rusty. Keeping that same domain, right? So what was the domain? This probably has to be in the answer. 16 is less than or equal to x less than or equal to 70. All right, there's part A. Part B, use a graphing calculator to solve the inequality here and describe how you use the domain to determine a reasonable solution. All right, let's go to the graphing calculator. I'll type those in as their own two separate equations. Again, this isn't about shaded region stuff, right? This is about comparing stuff. All right, this is the audio one. I need to find a way to differentiate them. I'll make one of them like bold. Make this one bold, thick. Minus 0.319x plus 15. Wonder who they studied for this. 0.0051x squared. It's probably a startling test. Oh, whoops, I was writing the wrong one. Minus 0.23x plus 22. Okay, we're going to go window range from 16 to 70, and I don't know. What's the other part? Reaction time. That's in milliseconds. So I'll keep the 1500 and see what it looks like. I can't see it, so okay. I guess our milliseconds are much better. I guess if I had 1500 milliseconds, that's 1.5 seconds. So that is a very slow reaction time. Let's narrow it down to like 100 and see what's going on there. Well, I can answer one part of this early, but let's make it a little curvier to see what we're going to talk about here. So the bottom one is the audio, and the top one's the visual, which tells us something. Because they don't intersect within this set, what was X? The age. So regardless of the age of the driver in this set, their audio stimuli their reaction time to audio stimuli is faster, it's more responsive, than their reaction time to visual stimuli. I didn't know which would be. I guess because there are other things on the road, but when you hear like a horn honk, I don't really know. I don't really know. But anyway, but those were the two graphs. So describe how you use the domain so use it to solve the inequality. Oh, we're asking for what values of x is the audio less than the visual? The whole thing, right? It's always less. So a of x is always less than v of x across the entire domain. That, not the all real number domain, but just that selected domain. Part C, based on your results, do you think a driver would react more quickly to a traffic light changing from green to yellow or the siren of an approaching ambulance? Explain. Well, the siren, well, it says approaching, but I mean, I guess the siren. A driver would react, and I didn't think that would be the case, more quickly to the siren of an approaching ambulance because that is an audio stimulus. Now I'm just thinking, okay, so like if I were racing somebody and it's like, hey, on green I go, and if the green was the same as the sound of the horn, whatever, and if one person had earmuffs and the other person got to look at the green light, the other person was blindfolded, safely, and got to hear the horn, I guess I'll do the horn. All right, number 48. I think six problems to go. How do you see it? The graph shows a system of quadratic inequalities. Identify two solutions of the system. So we're all about the overlapping shaded region now. Anything in here, not including the dotted lines that bound it, wouldn't be parts of the overlapping shaded region. So solutions include, I could say 2, 0, and let's do 3, 2. There you go. Part B. Are points 1, -2... Oh, that's... Oh. These are going by 2's on y. That's tricky. Does 3, 2 still work? Where's 3, 2? Yes, it does. All right, here's 2, 0. Here's 3, 2. Okay, that was a little tricky. Okay, are points 1, -2... So that's 1, -2. And 5, 6... I see what they're doing. Are they solutions of the system? Explain. They are not. No. No. These lie on dotted lines, dashed lines, which means they do not satisfy the inequality for which the boundary line is made. That means it's not a solution to the system. It needs to satisfy both, and if it's on a dotted line, even if it's bounding, even if it's part of the overlapping shaded region, then no. C, is it possible to change the inequality symbol so that one, but not both of the system, but not both the points in part B is a solution to the system? Explain. If one of them is, the other's not? No, you'd have to, wait. No, both would have to turn into, both would have to be solutions together, or neither. No. Either both would have to be solutions, or neither. They'd both have to be solid lines. You couldn't have one dotted and one solid. If a dotted dashed intersects with a solid, it's not a part of the solution to the system. It needs to be both. It needs to be both. Okay. Oh, I'm almost done. Mr. Robinson, you're almost done. Quit yawning in front of these kiddos. Number 49, modeling with mathematics. The length L in millimeters of the larvae of the black porgy fish can be modeled by this. Graphing calculator, perhaps? Where x is in the age and days of the larvae. Write and solve an inequality to find out what age a larva's length tends to be greater than 10 millimeters. Explain how the given domain affects the solution. So we got L of x. It's just so much to write. That trailing 0 means nothing. So x is between 0 and 140, or 40. Write and solve an inequality to find what ages a large length tends to be greater than 10 millimeters. So now we're going to put, this guy equal to 10, and then do the y equals this guy here. So we have to find out when it's greater than 10, so above that line. Okay, so I'm going to the graphic. Pardon me, I'm going to the graphing calculator here. We're doing that. 0.00170x squared plus 0.145x plus 2.35. The other one we're doing 10. Okay, so one's going to be the kind of thicker curve. The other's going to be that. So 10, let's put it up to 20. What are we between 0 and 40? All right, let's check it out. So there's our curve. Here's 10. Right near the end of it. Right near the end of it. All right, they intersect at 36.84 about. So x has to be, they said greater than 36.84. Is that what it said? Length has to be greater than 10 millimeters. X is greater than. And this is days. All right. What was the other part of the question? Explain how the given domain affects the solution. Well, they restricted our domain. I mean, if you see what the graph is, and I don't really know if you can tell from here, but if you see, clearly this one's a quadratic. Maybe you can't tell from the curve, but this is a quadratic. It's an x squared. So given that it's a parabola, it's going to, which way do I go? It's going to also come back up at some point over there. But that's not within our domain, and that's not a domain that we really care about. This starts at day 0. There are no negative days for in a live porgy fish or larva or whatever. So there would be a negative solution, but it should be ignored for the sake of the situation's context. So we're only going to deal with that positive solution that we found. Okay, number 50. Making an argument. You claim the system of inequalities below, where a and b are real numbers, has no solution. Your friend claims the system will always have at least one solution. Who's correct? Explain. I need to see which way they go. Given that they actually have stretch factors of 1, and given that you shade under, why wouldn't these be infinite number of solutions? You claim the system of inequalities below a and b in real numbers has no solution. So if this is x plus a squared and this is x plus b squared, I know they should be dotted, but I shade below this and below that. The overlapping shaded region, there's totally solutions all over the place. What's going on? What's wrong with this? Why would I make that claim? There's nothing wrong with this here. I'll leave that there. My friend is correct. So your friend, my friend is correct. Now keep in mind, these should be dotted lines. So I don't see any negative value. There's some positive values that won't be solutions. I mean, it depends on how this graph goes. Negative values will always absolutely be solutions. Any negative number. Any negative y coordinates. Any negative y coordinates will be solutions. Will be parts of solutions to the system. Period. I mean, plus some zeros and some positives, likely. Depends on what A and B are. Okay. They didn't say they couldn't be the same, so there's that. Number 51. The area... Ooh, that looks tricky. The area A of the region bounded by a parabola and a horizontal line can be modeled by A equals 2/3 base times height. Okay, I'll trust that. That might be accurate. Where B and H, I mean, by calculus standards, that probably is actually accurate. Where B and H are defined in the diagram. Find the area of the region determined by each pair of inequalities. Okay, so I'm going to use graph paper on both of these. I guess it's not so tricky. You just got to graph them. So A is y is less than or equal to negative x squared plus 4x. And honestly, I don't care about anything that's beyond the graph part. Now, negative x squared plus 4x factors to... Shoot, I wanted to fit the other one on this other side here. So let me do this. Y is less than or equal to negative x squared. Oh, I should have just factored the x. X. I thought this was a difference of two squares. X minus 4. Okay, so your y-intercepts of the first one are 0 and 4. And listen, I'm just going to be fast with this. It would be going like that and going downward. Now, y is greater than or equal to 0. Yeah, y is greater than or equal to 0 looks like this guy right here. So the overlapping shaded region is inside here. We need to determine that base and height. So the base is 4. The height is also 4. So the area of part A is 2/3 base times height, 2/3 of 16, which is 32/3 square units of area. I'll just leave it like that. Did they say round? No. All right. There's the first one. Second one. I want to factor this too. Sorry, I'm gonna write the factorization. X minus 5 times x plus 1, and the other one is y is less than or equal to 7. So the second one, I got x-intercepts at 5 and negative 1. 5. Oh, that's negative 1 and 5. It's a positive stretch factor. 3 away will be at negative 9 down. 3, 9, 4, 16. Now I do got to go up here, and this is actually where we hit y equals 7. So this is where I want to kind of cut that short. Boom. So greater than or equal to is above this curve, so inside of it. Less than or equal to 7, that's where it actually hits 7. Less than or equal to 7 is there, so the overlapping shaded region, let me actually thin this one out this time, or make it nicer looking, is this guy here. So we are talking about this base length of 1, 2, 3, 4, 5, 6, 7, 8, and this height from 7 to negative 9, that height of 16. So the area is 2/3 base times height, which is 2/3 of 128, which is 256 over 3 square units. I don't know what that is exactly, or it's approximately, but I'll leave it. All right, number 52, thought-provoking. Draw a company logo that is created by the intersection of two quadratic inequalities. Justify your answer. I mean, I kind of want to say no. I was thinking like Pepsi. Would a Nike swoosh count? That's not symmetric. Under Armour. McDonald's. I'm trying to think of ones that have the same like together. You can find like that. I was thinking of something like that. So maybe if I if I sketch some things out, I'll get one that works. Created by the intersection. I wonder what they're thinking of when they say this. You could probably still do Nike. If I did one that's like whatever and did one that's a little off, that's like whatever, it's not about symmetry, it's about a shift. Like this other one is kind of more like that. Now it's kind of Nike swooshed. Not. Oh, does that have to be a real company? Maybe not. Maybe you can just make one up. I think you just make one up. I don't think they meant a real company. So let's do that. Okay. All right, let's do I'll do like a rainbow, I'll do like a car wash company that has like a rainbow set of parabolas. So I'll do one that's going like here, and this will go to go over 5 down 5 is negative 1/5 x squared, like that. So that's one of them. Boom, and it's doing stuff. I probably should be doing better with it now that I have the equation. Over 1 down 1/5, over 2 down 4/5, over 3 down 9/5. I don't know what 9/5 is. Over 4 down 16/5. That's 3 and 1/5 or something like that. There we go. So that's a little better. Oh, that's terrible. I think the 2/5 one's a little bit, or 4/5 is a little bit off. Maybe that one's a little bit off. All right, so there's one of them. Boom, boom. Now let's do one that's sharper, but it hits the fifths again. Let's go up to 10, 7, 10. 10, 10, 10. And y equals, if I go over 5 down 10, no, that's weird. They'll all be weird. I already created one that's weird. Negative over 5. Instead of down 25, you're down 10. That's 2/5. I guess it's 2/5. Negative 2/5 x squared plus 10. So this is like that. So 2/5. What's 2/5 of 4? 8/5. It's 1 3/5. So it's like. Is that right? Am I doing that right in my head? I'm over talking about this problem. I can tell you that much. Over 3 down 18/5, which is 3 and 3/5. I must have done the 4/5 wrong. 8/5. Shoot. I don't know. I'm done. There we go. Okay, you know what? This isn't going to be a rainbow car wash. This is going to be a space... I don't know. It's kind of a cool logo. So this is less than or equal to this one, greater than or equal to this one, so that we have this intersection here. I think they said create a logo, like come up with your own. So this is going to be for... Pizza Planet. Space mini golf. I don't know why I spent so long on that. All right. I'm done with that one. Okay. Number 53, last question. A truck that is 11 feet tall and 7 feet wide. What? Oh, I guess it's not pickup, but I get it. Okay. Is traveling under an arch. The arch can be modeled by that where X and Y are measured in feet. Oh, wide. I was thinking like long. Will the truck fit under the arch? I hope so. Okay. Oh, these are weird questions at the end, I think. Okay, so here's the thing. Y equals negative 0.0625x squared plus 1.25x plus 5.75. The answer to the question on will it fit, there's a basis of, you see, the 11 feet tall matters, but so does the 7 feet wide. It's not about being 11 feet at the vertex of this thing, right? It's not about being 11 feet here. It's about that you have to account for the 7 feet wide. 3.5 feet on either side of the vertex. It still must fit there on that part at that 11 feet in height. So as far as what we're concerned on, and I don't know how much I'm supposed to do like by hand versus by graphing calculator, and I probably want to use graphing calculator more. But let's figure out where the x value of the vertex is. We'll go 3.5 both ways there and figure out if that point of intersection, if that's above 11 or not. So if I go to the graphing calculator, I'm going to let the calculator do a lot of it. I'm going to do negative 0.0625x squared. There's more than one way to do this problem. This is my approach. Plus 1.25x. I hope this truck makes it. Plus 5.75. And let's just do y equals 11. I don't even need to find the vertex in this case because I can let everything kind of automate itself. We'll go from 0 to 11 feet tall. That's 3 feet. Does this thing on here say it? Let's go from 0 to, I don't know, let's just go to 10 for now and figure out what happens. Let's go to 15 here. Oh, this needs more. 20. Okay. So, here's the question. We can answer it one of two ways. The first way I asked is, from the axis of symmetry, can I add 3.5 either way and still be above 11? I need to make clearance. Or, because here's the truck's clearance question. Is this width at least 7? I'll answer it the second way. Let's find the points of intersection. The first one, good. These are good numbers. So this is x equal, I don't know if it's true or not, but this is x equals 6. The other one is x equals 14. Okay, so good news for the truck. Now, you have to drive in the right part of it, but it'll fit. So these are the 2 points of intersection here. Now, I don't know if I'm doing the work well to write on here to support my answer. But 14 minus 6 equals 8. Whoops. 6 equals 8, and 8 is greater than 7. Basically, the truck's 7 feet of width needs to fit somewhere as a rectangle there within that. It has very little wiggle room. It has like a foot. It was like half a foot this way or half a foot that way to fit, and it needs to drive under pretty perfectly here. I mean, this better be a one-way street. This is very little wiggle room. The truck has the possibility of fitting. This is, I would never test that for myself because there are so many. I repeat it 10 times, I'm going to scrape at some point. What is the maximum width a truck 11 feet tall can have and still make it under the arch? So 8 feet. Now that's with its corners actually scraping the roof. It should really be less than 8 feet, but they did say a maximum. So I'm not going to say 7.99 or something. What is the maximum height a truck 7 feet wide can have and still make it in the arch? We didn't answer that question. So let's go back and look at it the other way. What's the maximum height a truck 7 feet wide can have? Now it's about finding the 3.5 from the vertex. Well, hold on. So what's this vertex? What were the two numbers? 14 and 6. What's halfway? So 10. 10 is halfway between 14 and 6. So axis of symmetry, x equals 10. Okay. 10 plus 3.5. This little 10 plus or minus 3.5 thing. 10 plus or minus 3.5 are 13.5 and 6.5. We have to find out what value of y we get with an x value of either of these. How do you find that out? You plug in either of these values for x. So I don't need the graphing calculator per se, but I need the table. I can just plug these in. So calculate the value at x equals 6.5. This doesn't have to do with that other line, by the way, anymore. The other number is 11.234375. Now, if I plugged in 13.5, I should get the same value. So 13.5, 11.23475. So truck's maximum height's around 11.23 feet. To fit with that, because 3.5 either way gives you the 7 feet of width. Max height is around 11.23 feet. It's just barely scraping by, right? So that's what that thing is there, and we're done. All right, guys, that ought to do it for this one. This is Mr. Robinson. Thanks so much for watching. Now, this is a newer video, way past all my other IM2 videos. Obviously, I'm recording IM1 and IM3 videos and stuff, but I haven't done them in a long time. So this is way past it, so I apologize for the rust or the complaining and yapping and things like that if you've kind of followed along this far. But I hope what I got helped you along the way. So, guys, thank you so much for watching this one. If you're following along in sequence of this, coming up next from this stuff would be like the chapter review and the cumulative assessment, or, chapter and cumulative assessment, things like that. And then you move forward. So, guys, thank you so much for watching. Take care. I'm going to see you in the next one.